To all the details. Sometimes I feel some minor details are a bit tedious. So yesterday in one of the advanced methods for the snakes, I skipped a lot of details and just showed the pictures. So if you want the details, please go through the notes or the book if you can access it. If I go through all of those details, it may be difficult or not so interesting for some of you. And minute details could be skipped because those are parts of the implementation. But if something is not clear, please stop and ask questions. If I go through something fast or skip some details, ask questions. Stop me and, okay? Let's look at another application in the processing of mammograms. And first we saw detection of the breast boundary. So when you have a mammogram, there could be other parts outside the breast that you want to get rid of, and you don't want those pixel values to affect further analysis. A part of the mammogram, I think you can reduce the gain a little. The sound is too much. A part of a mammogram that's important in the analysis by radiologists, important also in the analysis of mammograms for computer-aided diagnosis, but needs to be analyzed separately, is the pectoral muscle. The pectoral muscle appears in mediolateral oblique views, where the breast is compressed sideways at an angle. The other view is craniocaudal, top-bottom. So in the mediolateral oblique or MLO views, the pectoral muscle comes in, and the pectoral muscle has higher density and hence appears brighter in mammograms. And the edge of the pectoral muscle in many images is an almost straight line, but sometimes is curved. So we will look at two methods. One to fit a straight line using the Huff transform. The other to find a curved line, if it exists. If it is a straight line, that's okay too, no problem. And then we can segment the pectoral muscle and remove it, because that's not exactly part of the breast, but it needs to be analyzed separately. So this is a predominant density region in MLO views and can affect the results of image processing if you combine that region with the rest of the breast image. Because of the large density difference, and algorithms to detect tumors, if applied to both simultaneously, may not work well. So analysis of the pectoral muscle could be used to identify the presence of abnormal axillary lymph nodes, which could be related to breast carcinoma in some cases, or could be related to metastasis. So it is important to analyze it, but because of the large density difference, it is better to analyze it separately. So first we said, in most cases it's a straight line. If we can fit a straight line approximation, that is useful in other analysis, for example, detection of the nipple, but it might even be adequate to just remove that portion, even if it is approximated by a straight line. So it starts automatically by identifying an appropriate region of interest containing the pectoral muscle, and an approximate breast contour is obtained, and some delimiting control points are obtained for the detection of the skin air boundary, as we saw earlier. And 6 control points, N1 to N6, are marked automatically. So one of these slides should go. This one, if you can remove this. So that's the original image, and we saw the detection of the breast boundary. We have the breast boundary here, and these points N1 to N6 are marked. Or this is okay. That can stay there. Okay, that's fine.
I want that for video. That's
Okay. So let's go back. N1 is the top left corner of the boundary loop. N5 is the lowest pixel on the left-hand edge of the boundary loop. The boundary is already detected using the previous method we saw yesterday. N3 is the midpoint between N1 and N5. N2 is the farthest point on the boundary from N5 by Euclidean distance. N4 is the point that completes a rectangle with N1, N2, N3. And that could be inside the breast. And N6 is the farthest point on the boundary loop from N1. So these are the definitions. And the region of interest is defined by that rectangle. We don't need the entire pectoral muscle to fit a straight line. We take a part and fit a straight line to that edge. So we added some geometrical and anatomical constraints, as you will see. So first we apply the Sobel gradient and then the Huff transform. The Sobel gradient gives us the edge, and the Huff transform helps us in detecting straight lines. There could be multiple straight lines, little pieces that come from other parts. Filtering procedure to the accumulator cells in the Huff transform domain to detect the best possible straight line fit to the pectoral muscle. Enhancement of the peaks in the Huff accumulator. So there could be multiple peaks in the Huff transform, Huff domain. And if you can enhance the peaks, then you can separate the dominant peak from the others and helps in selection of the appropriate straight line. Detect the maximum value, and that should correspond, hopefully, to the pectoral muscle edge. So again, this is what we saw. Now, in this case, this box is enclosing all of the pectoral muscle, but it doesn't have to be so. Sometimes the pectoral muscle could go like that. But if you get this portion, it is adequate to fit a straight line. And in this case, the edge is an almost perfect straight line. I'll show other cases later. So the pectoral muscle is considered to be a straight line limited to angle theta between 120 and 170 degrees. And if the mammogram is of the right breast, it is mirrored before processing, so the pectoral muscle edge is always on the left-hand side. So the pectoral muscle intercepts the line segment N1, N2. It has to cut there because this is the edge of the breast. So there must be an intersection there. The pectoral line is present in partial or total length in the rectangle. In this case, the whole thing is there. In other cases, not all of that. And the pectoral muscle is always denser than the rest of the breast, and it is relatively homogeneous. Whereas inside the breast, there is heterogeneity. Sometimes the entire breast could be fairly homogeneous in density, but this certainly is homogeneous. There could be lymph nodes present there, but that could cause a small deviation. So we then define this coordinate system, take the center of the image, and angle theta is defined this way with reference to the horizontal line through the center of the image, and rho is the distance of the straight line along the normal in that manner. So those are the coordinates for the Huff transform. And A is the area of the pectoral muscle that is obtained in the process. A Gaussian filter with sigma x sigma equal to 4 is used to smooth the ROI, so that we're not interested in the details within the breast, the tissues. And Huff transform is applied to the Sobel gradient. If you take the Sobel gradient directly, there could be noise and variations due to the muscles and tissues in the breast. So you don't need that. The Huff transform is this, which we have already seen. Here, x0, y0, the center that is chosen is subtracted, just for reference. That's the origin in this representation. The Huff accumulator is quantized to 45 bins of 4 degrees each. To create the discrete accumulator, you have to discretize the variables rho and theta. So you choose some quantization. We chose 45 bins of 4 degrees each. And the accumulator cells, they're called accumulator because you keep putting a vote into that. Every time a pixel is analyzed, is it on the edge or not? Is it on a straight line or not? If it is on a straight line, for that bin in the accumulator cell, you put 1. You add 1. But you don't have to always add 1. You can add the strength of that pixel corresponding to a line, like a fuzzy membership. So here we use the magnitude of the gradient instead of unit increment. If it is a strong edge, it contributes more in the Huff domain at that coordinate rho theta and xy coordinates as we have used. So this way, it's a non-uniform or selective incrementing of the Huff transform accumulator. It helps in detecting stronger edges and suppress weak edges. So theta values only in 120 to 170 degrees were considered in the analysis. But we don't need 0 to 180 degrees. You don't have to go the whole range because the pectoral muscle will be like that. It cannot be like this. So it could be maybe like that. It has to be vertical, and it cannot be vertical. So it will be, there is a certain range depending on the geometry you have specified. So the Huff transform doesn't have to be computed for all theta and all rho. Rho also is limited by the size of the mammogram, and so this is not just discretized, but also you put spatial constraints in the definition of the Huff transform accumulator. And then we apply a filtering procedure in the Huff domain. In the Huff domain, we have some patterns, as you saw. Straight lines have these sinusoidal. Every pixel on a straight line gives you some sinusoidal pattern, and if there are a number of pixels having the same parameters of a straight line, then those curves will intersect at one point, give you a large value there. But there are many straight lines possible. So there will be many peaks. So how do you choose the correct peak? For that, there is a filtering procedure. All lines intercepting the top of the image outside N1 to N2 or with slopes outside the range 120 degrees to 170 are removed. We are not interested in those lines. They cannot be the pectoral muscle. The x-axis corresponds to 0, and we have seen that coordinate system. And then the remaining accumulator cell values are weighted. You apply a weight using this alpha equal to mu over sigma square A for that rho theta value. Mu and sigma square are the mean and variance of the gray levels in the area A of the pectoral muscle, defined by the straight line with these parameters. So depending upon which line you choose, you will get a certain mean and sigma square. And you apply that as a weight. And the procedure will enhance the Huff transform peaks that define dense and homogeneous regions. If the line comes too much into the breast, then there will be more variance. This will increase, so the weight will decrease. If the density is not high, if breast tissue is included, this density becomes low. Then that weight will be reduced. So if the correct line is found, mu should be maximum, sigma square should be minimum. So this weighting helps in distinguishing between various lines that could be detected in the Huff transform and choosing the correct one corresponding to the pectoral muscle. I'll show examples soon. Okay, so here we have the Huff transform domain. This is rho, 0 to rho max, 0 to pi. But we're not going 0 to pi, we're only using this much. What did I say? 120 to 170 degrees. We are using only this portion. And within that, we are cutting off many other lines. Each point here represents a line in the image domain. So by rejecting all of these other points, we are rejecting some lines that could be detected if you were to find all the peaks here. And further, by applying the weight, only these are highlighted. And among these, you find the maximum. So in the Huff space, we can put more and more constraints depending on what you want to detect, where is it located in the image, and its properties. Not its properties, but the part it would separate from the rest of the image. So here, we are going, this is 0 to pi, but we are using only 120 to 170 degrees. And this is after removing lines intercepting the top of the image outside the region N1 to N2. Let's go back and see here. There could be some line it goes like that. And if it goes outside this, you say, I don't want that line. If the line includes breast tissue, then mu and sigma square, mu will be low, sigma square will become large. So in that manner, you put many constraints. and the processed half space is that. After weighting, in that you find the maximum. And the result is that line for this mammogram. I'll show more later on. You don't get such straight line edges always in the mammogram, but in this case it works well. So in some cases the boundary is not a straight line, so it's a curved line. There could be multiple line segments of different orientation. So we applied Gabor wavelets for directional analysis. It's a little too much. You don't need Gabor wavelets here, but we have again put constraints to minimize computation. We will look at Gabor filters later in more detail in the chapter on analysis of oriented patterns. But Riccardo Ferrari, who did his PhD with me, he applied Gabor filters with many constraints so that computation could be minimized and pectoral muscle edges that are not straight lines could be detected efficiently. So a bank of Gabor filters is used to detect piecewise linear structures, that is, making up the pectoral muscle edge. Here the region of interest is defined to contain the entire pectoral muscle region, because you cannot extend as a straight line like we did in the first case. Let me go here first. So here is the pectoral muscle, which is a curved line. Now one could say, well, let's fit a curve, but in many cases there are other curves and it changes curvature. So in order to account for all possible shapes of the pectoral muscle edge, we said let's use Gabor filters, but we know the angle range. So the Gabor filters don't have to go again 0 to 180 degrees. So we said we'll just cut the mammogram in this manner by finding the farthest point from this. The mammograms are always arranged so that the pectoral muscle edge is on the left-hand side, and find the edge of the breast boundary there and draw a straight line and remove everything else. So now the pectoral muscle, which is on the left-hand side, will be there. Sometimes it can come up to here. It is supposed to go at least more than half the size, perhaps up to 3/4 of the height of the image. That's a requirement. So this doesn't meet that requirement. That's what Dr. Desertil told us. So this is defined automatically as a rectangle formed by the chest wall as a left-hand edge and a vertical line through the uppermost point on the skin air boundary. And then we apply image decomposition using Gabor wavelets. I describe the wavelets now. Then computation of the magnitude and phase images by vector summation, phase propagation, detection of boundaries by searching for pixels with opposite phase orientation, correction of disjoint boundary segments, and removal of unlikely pectoral muscle boundary candidates. Those are the steps. So this is the first step of delimiting the processing portion. Now let's look at Gabor wavelets, but we will see this at least 2 more times in chapter 8. Gabor wavelets are Gaussian functions. This part is a Gaussian, modulated by a complex sinusoid. But this could be changed to just a cosine function or a sine function as you wish. This includes both sine and cosine. So it's an exponential. If you just take this part, it is a Gaussian. There is some normalization factor. This is not important in image processing because you will be transforming and thresholding. But this part gives you the modulation. So it is a Gaussian function which is multiplied with the sinusoid. So you get a positive main lobe and negative and positive side lobes going to infinity. Then you can dilate, you can treat these as wavelets. You can also treat it as just a function. Take the Fourier transform, you get a bandpass filter. There are the scale factors, you adjust them, and you will see the bandpass nature of the filters in a moment. And you can use whichever filters that suit your application. You can have as many as you want and make a bank of multi-scale, multi-orientation filters. But in this case, for his own interest, Ricardo, he said we will use the wavelet formulation. Doesn't have to be so, but that's what he did. And in the case of wavelets, you need a scale factor and you need rotation, in this case for directional analysis. So psi mn xy is a to the minus m psi x prime y prime, where x prime y prime are the rotated coordinates. Some origin x naught y naught. This is simply the rotation transformed by angle theta n. And do it for all angles of interest. Okay? Scaling, rotation. So theta n is some n pi over k, as many steps as you want. In the frequency domain, you get bandpass filters. The Fourier transform for Gaussian is a Gaussian. You are modulating it and rotating it. Rotation in the space domain is rotation in the frequency domain by a corresponding angle. And scale factor will shrink or expand that Gaussian. And the modulation will place it at a certain position depending upon the modulating function frequency. So it turns out to be, this is a Gaussian, but U is shifted by this W, that frequency, the modulating frequency, capital W. This is just a Gaussian. That is multiplication by another exponential j2 pi wx, which is cosine and sine. So in the frequency domain, UV is a frequency domain, you have another Gaussian shifted in one frequency. And these are the scale factors. These scale factors are inversely related to the scale factors or sigma in the space domain. The design strategy is to project the filters so as to ensure that the half-peak magnitude supports of the filter touch one another. So these are Gaussians. Each one is a Gaussian in the frequency domain. But it goes on forever or to the end of that, whatever the array is. But at half of the power point, you say, okay, that's enough. And you want the next Gaussian to sit at that point so that you don't get gain less than half when you use multiple filters. So this is how it looks. There are 4 scales. As you scale the function, the Gaussian function, each one of these ellipses is a bandpass filter. The position of that bandpass filter is determined by the scale factor, low frequency, medium frequency, and high frequency. And the angle is given by the rotation. And W determines these placements. So we have these multiple parameters, A, sigma, X, sigma, Y, and W, and the theta. So if you want to have the full range, then you would use all of these filters. We are showing here S equal to 4 scale factors, K equal to 12 angles. And these are the UL and UH are the frequency cutoff parameters. If you want to get output in all angle bands, then you would use all of these filters, there are 48 of them, bandpass filters. But we know that the pectoral muscle is only in that range, some range position in that angle. So we only use these perpendicular to that angle in the image domain. So these 3 angles and 4 scales, we use only those filters, or the output of those filters. And the DC gain is set to 0, so that intensity information is removed and you meet the conditions required for the wavelets. So this is 0 here. Depending on the scale factors you use, you will get different shapes of those Gaussians in the frequency domain. So you have this parameter A, UH over UL to the power of 1 over S minus 1 scale factor and the cutoff frequencies. In the frequency domain, sigma U, sigma V are related to those other parameters. You don't have to read all of that. But they are related to the parameters you specify in the space domain and the other design parameters I mentioned. So UL, UH are the lower and upper center frequencies of interest. K and S are the number of orientations, number of scales, and sinusoid W is set equal to UH. Now, we are dealing with real images with positive contrast. The objects of interest are denser than the background. So you don't need sine waves in the complex exponential. You only need cosine functions, so you only take the even part of these functions. You don't need the complex wavelet. So there are some design parameter choice made here. I'll skip all of those and go to the detection part. After computing the phase and magnitude images by vector summation, there is vector summation of those 12 outputs. Now you have different scales and different angles, and how do you combine them? You use angle as the phase and the magnitude of the Gabor output at that location as the magnitude in composed vectors, because you only had 3 filter angles. The edges could be at any angle in between them. So you use vector addition. The magnitude AXY and phi XY phase at each location are used to represent edge flow or some kind of an oriented pattern. So there is a phase propagation algorithm. I won't go through this. You can read this later on. But instead, let me show here. This is the pectoral muscle edge, and you have these vectors indicating the direction of what he called phase propagation, the phase of these outputs of the Gabor filters combined as vectors. So when you have opposite phase, then that is where you have the edge, because you have the gradient this way and gradient that way, and that's where the edge lies. So by finding these pixels, and there is one more set here, we get the edge, or edges, as many edges as are present in the image. So here we have the result. Again, I'm skipping some parts. You may read them, or I think the pictures will tell the story. Minor details need not be of concern at this time. So here we have the pectoral muscle. This is the part of the image chosen for processing. There is a little bit more of the breast image there that was removed initially. And this is the Gabor magnitude output, the edges, and this is after some processing to remove other parts that are too far from this boundary and they don't touch the upper boundary. The pectoral muscle edge has to touch the upper boundary. So these other pieces can be easily rejected. So you do get multiple lines from the Huff transform because there are multiple peaks that pass all the criteria. So out of all of these lines, which one do you want? You take the longest one, and it has to cross there, it has to cross here. So that is the pectoral muscle edge. There is something here which most likely is a lymph node, but the edge goes through that. I'll skip some of these parts. We don't need these. Let's go to look at some results. The false positive and false negative pixel counts were computed for all of the images in the test data set in relation to the pectoral muscle boundary drawn by a radiologist. And the results were evaluated visually by the radiologist and also in terms of these. And the images were ranked in terms of false positive and false negative both being less than 5% or 5 to 10% or more. And the results with the Huff transform, there were 66 images having false positive, false negative greater than 10%. With the Gabor, that reduced to 17. So the output of the Gabor filter is a better approximation of the pectoral muscle. So some more examples. That's using the Gabor filter. That's using the straight line. So the pectoral muscle edge comes here. The straight line doesn't catch it, but this one does. This is a good straight line. Gabor filter works. Not a perfect straight line. The straight line is giving a little extra breast tissue there and missing some pectoral muscle edge there. In some cases, there could be two edges to the pectoral muscle. There could be a major muscle and a minor muscle. And then there could be confusion. But the method worked well. We got this edge here by choosing the longest line. Both of these lines meet the conditions. Well, here it doesn't. It doesn't meet here. It meets the top. So if you were to put the extra condition, it has to cross here too, then that goes. And all of these lines fail. Okay? Any questions or comments about this? Riccardo Ferrari, he did a lot of work on detection of the breast boundary, pectoral muscle, the fibroglandular disc, Gaussian mixture modeling, and bilateral asymmetry for his PhD. That's a lot of work. We wrote many journal papers based on his work. So all of this is based on his PhD work. The next one is fuzzy set based fusion of contours and regions.
When applying this Gabor filter on entire image, there could be something inside the breast, some calcification or something get detected.
Not calcification, but the fibroglandular tissue. Fibroglandular tissues, they will come up later on in chapter 8 in the detection of tumors. Fibroglandular tissues will have sort of curvilinear structure patterns. So if you use Gabor filters for the entire image, you will detect the fibroglandular tissue patterns. And we have used them in the analysis in the detection of architectural distortion. I'll go into that at the end of chapter 8. So yes, Gabor filters can detect many other things. Here, it is an overkill to use Gabor filters.
White patches were there in the bottom side of the image.
Yeah. No, but we were looking for straight lines only in the half transform case. In this case, we put other conditions that these lines must cross the upper boundary and the lower boundary. And the lines that you get within the breast will be short lines. So they will all be rejected. I showed some of them passed the test. But they will not be as strong as the pectoral muscle edge. But if you apply the Gabor filter, and we have done that, the full range of Gabor filters to the full mammogram, then we can detect all fibroglandular tissue. And we can use that for the detection of asymmetry and architectural distortion. So that comes up again later in chapter 8.
Is there any use of using multiple filters on the same image?
Multiple?
Filters, like different filters on the same image. Can you use it?
We have used multiple Gabor filters, different orientation and scale here.
You are
But
just changing the fields, right? On the same parameters, you are just changing the parameters on the Gabor filter. I'm asking like Gabor filter or half transform Gabor filter or problem. Is there any problem in that or advantage in that using it?
other filters were used for example, low pass filtering to remove noise and so on. But it depends on what you want to detect. Certainly, there is nothing preventing one from applying multiple different types of filters and getting their outputs and combining them. But it depends on what you want to detect and what you want to do. So in this case, we want to only detect edges. And Gabor filters, being bandpass filters, will detect edges. As I said, you don't need Gabor filters in this case. But then we limited the range, angle range, so we didn't use the entire angle range. And we used vector summation using only 3 angles. So computation was not that high. We wanted multi-scale. Even that perhaps is not required here. Multi-scale just for the edge is not necessary. Whereas if you want to detect all of the fibroglandular tissue within the breast, then you need multi-scale and full orientation, 0 to 180. And if you want to apply other filters before, you could do for pre-processing. Along with Gabor filters, I can't think of which other filter you would put, but it depends on what you want to detect.
So there's no edge flow map, right? It's from edge flow map.
Yeah.
Is it in a Python code to get edge flow map?
Oh, this work was done long ago, and if you want, I can give you the email contact for Riccardo Ferrari. He has the code. I don't keep the code. But this was done more than 25 years ago. I don't think it was Python. It would have been C++ or something. I don't look into the code of my students, but I do check the results. I sit with them and look at the results. And the code is theirs. And in most cases, the next student who comes will say, oh, that code is bad, and write a new code. And the next student comes and says, oh, that code is bad. I have seen that repeatedly.
I've seen the previous edges were there, but along with that there was an edge flow map. I just want to know how that is the code or something like that. To display.
If you want, please send me an email, and I'll connect you with Ricardo. He's in Brazil.
The advantage with the Gabor map, like multi-scale and multi-orientation.
Correct. But scale is not important here. It's only the edge you want. So there is no scale in the edge. But wavelets were topic of interest at that time. Gabor filters in multi-scale formulation was a topic of interest, so it was used. But perhaps it could be simplified further. You don't need all of that information. But it worked, so it's there. So this is going back to the work of Denise Gugliato. She's also in Brazil. And we did some collaborative work on fuzzy set image processing or fuzzy set based image processing. I showed you fuzzy region growing and then getting the contour, and then a fuzzy region growing method that gave a region, a fuzzy membership region for the tumor. So one method gave a contour, another method gave a fuzzy region with fuzzy membership with no contour. And later on you will see another method, another student of mine developed to detect tumors that gives another boundary. So in your bank of programs, you may have multiple programs to detect something. And one gives a contour, one gives a region, another gives a fuzzy membership region. So which one do you take? Or could you possibly combine them all and get one result that is better than any one of them? So for that, Denise said we will develop a fusion method where we can take all of these and fuse them by using some operators for fusion. Now some of the terminology here is computer science based, so I had a bit of difficulty with that, but let's see how it goes. So can the problem benefit from the use of multiple approaches to detect something? And when you get multiple results, instead of looking at all of them, can you put them all together and get possibly a better result? So we already saw one to get a contour, another to get a fuzzy region. So what is a fusion operator? It says you have fuzzy sets defined in this manner, and you map to 0 to 1, and n greater than 2 or equal to 2 will represent the number of sources of information. So there are conjunctive, disjunctive, and compromise operators in fusion. An operator is conjunctive if when you combine a number of these inputs, the result is less than equal to the min of all of these put together. That's a consensus. It is developing a consensus between these. It is a generalization of intersection, and it is severe behavior because the result is lower. Disjunctive takes greater than equal to max of all of these. And it is permissive, it allows all of these opinions. And it agrees with the source that offers the greatest measure and redundancy between criteria. And a compromise operator is something in between. And it is cautious behavior. So you have these sources coming from multiple methods, contour, region, and so on. But how do you include or combine a contour with a region? So these are context-independent, constant behavior operators. They maintain the same behavior independent of the input variables. So let's look at this picture and then we will see. So there is a contour. SC is a contour. SR is a region obtained by region growing. And there could be some artifact there. The region may include parts that are not included or members of the region. So a fusion operator designed to aggregate such entities should produce a third entity that takes into consideration the inputs and is better than either input. So the fusion operator must be able to identify regions of certainty and uncertainty. Where do you have high certainty and where do you have uncertainty? You have high certainty here and along the boundary. But you need to include the others too with a fuzzy membership. So there are 4 situations here. The points on the contour, points inside the contour, points inside the region, and points of the region inside the contour. That is obtained by contour detection, and this is by region growing. So all pixels in this region are members, and only pixels on the boundary are members. So you need a mapping. So there is a membership degree P, and there is a mapping that goes from SR to I in the range 0 to 1. This function is 0 when the pixel P is inside or outside the contour. It's equal to 1 only on the contour. Now you may say, well, everything inside the contour belongs to the object. That's possible, but certainty exists only on the contour because that's what is given to you. And it possesses a high value and P is on the contour. Similarly, it belongs to the region and it is low or 0 when it does not belong to the region from the other input. So the fusion operator, 4 situations arise. P belongs to the intersections of the two inputs, SR and SC. In this case, P belongs to the final segmentation with high membership. Both are telling that is inside. So the sources agree with respect to the inclusion of P in the final result. It is certainty. And the second P does not belong to SR or belongs to SR with a low membership if it is a fuzzy region and is inside the contour. So this is a case of uncertainty because we don't know if this intersection, let me just see here, it does not belong to SR, okay, it's outside the region. All belongs to SR with a low membership degree. So the region growing method says the membership is low. So there is a case of uncertainty. P belongs to a contour line of SC and does not belong to SR. Then this is also uncertainty. The fourth one, P belongs to the region with high membership but is outside the contour. So this is also uncertainty. So going back to that picture, we have these 4 situations. Certainty here, the others are uncertain. Here we are on the contour, but the region doesn't include that. Let me go to some of these The fusion operator is defined by a finite automaton that aggregates the n sources by having this pair H. H is made up of these points that are fusion operators, and they map the input to the range 0 to 1. I'll skip some of these details. You could read them later on. I don't want to read all of that. There are just the rules there. Let me. Okay. So we had the contour. The contour drawn by the radiologist is shown for reference here. I showed the contour obtained by segmentation earlier and the region. When you combine them, you get this. And if you were to compare with the previous picture, you see that the fuzzy membership computed by fusion, which is shown here in different levels of gray, is having a high value of membership inside the contour given by the radiologist. By the way, that contour by the radiologist was drawn independently. He didn't have this figure or this result. And there are low values here, but there is not much outside. This part was included in one of the methods, but now these pixels have low membership value. So in a way, this result is better than the other two by using these conditions. This is a benign mass case where you don't see many pixels with low membership, and the high membership values are all included within the contour given independently by the radiologist. I showed these results earlier. You could compare them with those figures later on. Here is another case. There is a dense mass here, and let me go and check which is which. Contour extracted by fuzzy set. Black is the radiologist and C is fuzzy region growing. Okay. So the black line is the contour drawn by the radiologist. The white line is obtained by region growing using the fuzzy set pre-processed image. So it includes the mass, but there is some excess material here. This was obtained by the fuzzy region growing method, which is not bad actually, except for a little bit there. Most of it is contained within the reference contour. And when you fuse them, what was outside, the excess region in the contour now has low membership. So some of that was outside the contour, but not in the fuzzy region, is not exactly rejected, but the membership is low. There are many pixels around the boundary that have low membership. So we found that this was a good indication of malignancy of the mass. This is a speculated malignant tumor. And go back, this is benign, and this is also malignant. So in the case of a malignant tumor, you see pixels around the boundary having low membership because the boundary is fuzzy, the tumor is not well defined, and the tumor is spreading. So fuzzy membership in this case does relate to the malignant nature of the tumor, whereas in the case of a benign mass, the membership is sharply defined right up to the boundary and not much beyond. And here, this is also malignant, and you do have a number of pixels around the boundary that have low membership. So this we took to define a measure of fuzziness. If there is fuzziness in the boundary, I'll just skip all of these definitions. We don't need this for now. The result was evaluated by just comparing these images before and after fusion, so I will not go through that. There are some numbers here that are not important, so I'll just skip all of these for now. If you want, you can read those later. So to end this chapter on detection of regions of interest, we have looked at several methods, and we have studied methods to detect objects of known characteristics or geometry, and how to improve initial estimates. After regions of interest have been detected and extracted from a given image, they may be analyzed further to represent features, or in terms of representation, to do feature extraction, get some parameters that represent the distinction between the categories of interest, shape, texture, whatever, and those should help in pattern classification and image understanding, eventually leading to computer-aided diagnosis. Now, how do you characterize regions, which is the topic of the next few chapters? There are external characteristics, boundary or contour morphology or shape, boundary roughness, boundary complexity. And typically we would want the boundary descriptors and any descriptor in general to be independent or invariant to translation, scaling, and rotation. If it is rotated or if it is translated, it should be the same. Scaling, if the object is that big or this big but has the same shape, that is, take a picture from here or from a distance, the characteristics you measure must be the same, must be invariant to those. Internal characteristics of the region, grayscale, gray level, color, texture, statistics of pixel population of what is inside the region. And then after you extract the features, you want to compare the regions in terms of similarity or dissimilarity. Are these regions similar or not? You can do direct pixel by pixel cross correlation, template matching, and so on, but we don't want to work with pixels anymore. We want to extract features that combine all the information present and be independent of individual pixel values, and instead use the features that we have designed based on what we have learned from the domain experts. So for that, you could use distance measures and correlation coefficients between the feature vectors, not the pixel values. But that is pattern classification, which I have in the last chapter in the book, but my book is not on pattern classification, so there is just a quick review of basics of pattern classification. But the best book available is Duda and Hart. A relational description. You have multiple regions that you have detected. What are the placement rules? How are they placed? Some kind of a grammar to connect them. Structural description and syntactic analysis. Describe each one and then describe somehow how they are placed, how they interact, how they are, what is the interplay between them, such as a cluster of calcifications. You detect each calcification, but then you have to put all of the information together. How many calcifications did you detect in the image? Are they placed in a small area in a cluster, or are they distributed at random? And if they are placed along a straight line, like a duct. So these are important, and that would be the relational description between multiple regions that you have detected. Not much in the case of tumors, but tumors could contain calcifications. So you want to know if a tumor you have detected contains calcifications. So that would fall under relational description. That finishes the chapter on detection of regions of interest. I skipped a lot of details. Reading them or going through them doesn't fit in a course like this. You may read them if you are interested in those. What else did I want to say? That's about it. I have skipped a lot of details here. I want to keep some time, if possible, to include another research seminar later. And I want to go through texture and oriented pattern analysis in detail. In the files I have sent for you, you have chapter 7 and 8, and there is a file called texture analysis, which is just a few parts extracted from 7 and 8 that I give as a seminar on texture analysis if I don't have the time to go through the material in detail like this. But I think we will have enough time to go through 7 and 8 in detail as much as possible. I'll skip some parts again to keeping the time in mind. But next we have analysis of shape, which will take up. Shall we break now? It's a little less than 1 hour after we started, but let's take a break, have some coffee or tea, and come back. 30 minutes?
Yes, 30 minutes.
Okay, thank you. How do I get rid of this side? Why am I getting the side here? Okay, I just mentioned this thing about how to sculpt an elephant. I just made some pictures. One of our colleagues in radiology was just, I don't know if he meant it really or just made fun. We were asking him, how do you find the boundary of your tumor? He said, well, I look at the whole image and this is liver, this is kidney, this is bone, I remove all of that, and if anything remains, I examine if that is a tumor, and then I'll say that is a tumor. Then I remembered this joke about how to sculpt an elephant. So somebody asked this person, this is in Mamallapuram, somebody went there and asked, oh, how do you make all these beautiful sculptures? How do you sculpt an elephant? So he's making that there. It's not so easy, but the algorithm is find a big rock. And this is also from Mahabalipuram or Mamallapuram. My nieces and nephews are sitting under that big rock. It's been there for a long, long time. I hope it's still there. And remove everything that does not look like an elephant, and that's what you get. So, just for fun. Okay, that is segmentation. Now back to real stuff. So next chapter is on analysis of shape. We have completed the image processing steps. We said in segmentation, the output may or may not be an image. If you cut a piece of an image and give it, then yes, it looks like a picture. But if you just draw the contour or give the fuzzy membership, it's not anything like the original image anymore. But the next step, we go away even from that. So the output of the remaining algorithms could be some features, some numbers, such as when you apply shape analysis to a contour, you're not giving a contour back, you're giving some numbers back. And those numbers could be normalized to the range 0 to 1 or 0 to 100 or whatever, or could be open-ended. Depends upon the design of the algorithm. So why do shape analysis? There are several human organs that possess readily identifiable shapes, like the heart. But then the heart is not like this, or you do that, well, it's not like that. The heart has a different shape. And kidneys, the brain, the bones, and in most cases the same average shape holds. That's how they make all these so-called ready-made dresses, we have certain ratios that are almost constant for most of us. But with the kidneys, some say kidneys are bean-shaped, but then there are kidney beans that are kidney-shaped. So which one comes first is up to you. But diseases can affect the shape and structure of organs. Morphological changes can occur due to diseases. Or there could be a tumor that pushes and somehow presses against some organs and their appearance is changed, like that neuroblastoma tumor I showed. So what are these shapes? And why is shape important? Even in abnormal situations such as masses and calcifications, there are differences between benign and malignant conditions. Benign is not normal. Benign means some disease that is not cancer. Malignant means cancer. Well, this also started misbehaving now. Okay. Most benign masses, I have shown some examples, appear round and well circumscribed with smooth and sharp borders. Sharpness is not of concern right now here. Some benign masses may be macrolobulated, big lobules. Malignant or cancerous tumors are typically ill-defined, meaning they are not very clearly separated from the background visually, and possess rough or stellate star-like shape with strands and spicules appearing. Now, previously the word stellate was used, stellate meaning looking like a star. But then star is a beautiful thing with all these songs and so on. They said, no, tumors are not beautiful things, they're not stars, so they tried to remove that word out. So it is not stellate, but spiculated. But most of the grammar, spelling correction software in Word and other things, they don't know spiculated. I write spiculated, it changes to speculated. And I write tabla in my music, it changes to table. So spiculated. Spicule means something that is radiating out, finger-like protrusion. Some malignant masses may be microlobulated, small lobules. So shape is a key feature in discriminating in these cases and also in pap smear tests. But biological entities exhibit a broad range of variation or variability around some general shape. They're not all round. There's some variation around that. They're not all spiculated. Some may have a few spicules, some may have many spicules. The number of spicules is not important, but the fact that it is spiculated. Imaging geometry, 3D to 2D, and superimposition of multiple structures in the image, in the object rather, in the breast. When you compress the breast, there could be several fibroglandular tissues and ducts, and if there is a mass that is round, if these superimpose in the image, it might look like spiculated. So you must be able to separate the mass from the other confounding or overlapping structures. So these factors affect shape analysis. Still, shape analysis is useful, as you will see. So how do you represent shapes and contours? Typically, we deal with closed contours. So you go around and come back to the starting point. So the XY coordinates of the pixels along the contour. You don't normally keep track of the gray value or density along the contour, just the shape. So it's a binary image, if you want to call it so. So a contour with endpoints could be written as xn, yn, n going 0 to n minus 1. Not exactly an image, but it needs 2D for display. So you could show it as a binary or bi-level image. Basic things. A point of reference is a centroid or center of mass. Many dictionaries don't recognize centroid. We use it so often. Center of mass is used by some people, some researchers. Centroid doesn't seem to be commonly used, and dictionaries don't recognize that. But anyway, average all the x coordinates, average all the y coordinates. That's a centroid. And that could be a good reference point in shape representation. If you take the distance of every contour point from that centroid, xn minus x bar square, yn minus y bar square, and that's just the Euclidean distance, then you can express a signature of the shape as a 1D function, this dn. And you can plot it as a signal, and you may apply signal processing algorithms if you wish. You can also define a radial distance signature by drawing from the centroid a line and find where that line intersects the contour and get that distance, and go 0 to 360 degrees and then plot that distance. But then if you have a rough speculated contour, and if you draw a line from here, it could intersect multiple points on the contour, then that method fails. So which one of those will you take? So that has limitations. For irregular contours, such a signature may be multi-valued for some angles, meaning multiple intersections with the boundary. So going around the contour more than once generates the same signature, so it is periodic, which means you can use Fourier series instead of the Fourier transform, and there is a notion of harmonics. Going once around the circle is one cycle. If you go again, it's the same thing. But then if you break that signal into components using the Fourier series, you have other harmonics of that fundamental frequency. So here is a representation of a contour, the centroid x bar, y bar, and z0 equal to x0 plus jy0. That's the starting point, point 0. x0, y0, x1, y1, x2, y2, and so on, xn minus 1, yn minus 1. You want to go clockwise or counterclockwise, it depends upon your convention. Now, z0, z1, z2, they are complex representations of the x and y coordinates put together as a complex variable. That is useful in computing the Fourier series that we will see later. The distances I mentioned from the centroid, d0, d1, d2, dn minus 1, they form what is called a signature, a 1D function. So this is a macro-lobulated benign mass. It's not a circle. If it is a circle, this will be a straight line. The radial distance will be the same for all points. But because it is varying from here, small and long distances and so on, if you plot it, you get this sort of, not a sinusoid, but something like that. This is called a macro-lobulated mass. It's not a circle, but you can say there are three lobules, maybe 1 and 2, maybe only 2. Maybe this, I don't know if it is a lobule. Maybe this is a lobule 1 and 2 and 3. So 3 big lobules. And you get a low frequency signature. Whereas if you take a highly speculated malignant tumor with so many protrusions, that's a centroid, you plot that function dn, you get so many variations. The number of points is different. Here it's more than 3,000. And here it is about 800. That doesn't matter. You normalize, call this 0 to 1. The size of this doesn't matter. You throw it out somewhere. So normalize, divide by the maximum and make that axis 0 to 1. Going once around the contour is 1. This distance is some distance, some number, depends on the sampling resolution. It's not important. The shape is important. The value of that distance is usually not important. In the 1960s, a chain coding method was proposed by Freeman that was used for many years. It's not so commonly used nowadays. The question is, how do you efficiently represent a contour in terms of its coordinates? So you start from you take up some arbitrary starting point, and then they select a direction of traversal, clockwise or counterclockwise, and use a code to indicate the manner of movement to go to the next point on a discrete grid. The movements are either with 2 bits, 0, 1, 2, 3, just left, right, up, down, or using 3 bits, including the diagonal 0, 1, 2, 3, 4, 5, 6, 7. So to represent this, depending on which one you choose, you need 2 bits or 3 bits per step. But this will be a coarse representation. So coarse representation, and the others are given relatively. as to how you moved. So to reconstruct or plot the contour again in the correct coordinate, you need the starting point. If it doesn't matter, you can draw it using just the code. So the chain code facilitates more compact representation and gives you some data compression. But nowadays, that data compression is not of interest, but what you can derive from the code is important. So you require only 2 or 3 bits per contour point. So there are a few advantages. The code is invariant to shift or translation because the starting point is kept out of the code. To a certain extent, the chain code is invariant to size or scaling. Contours of different sizes may be generated from the same code by using different sampling grids. You're given the code, you're given this step as to this way or that way, but what should be the step size? You make the step size bigger, you get bigger and bigger contours of similar shapes. Not exactly the same, but mostly the same. A contour may also be enlarged by a factor of n by repeating each code element n times. So instead of changing the step size, you may say, I will do the same thing twice or thrice, and that also leads to enlargement or expansion. It may be shrunk to half the original size by reducing pairs of code elements, averaging to single numbers. But then, what is the average of these? You don't have that in between. If you have 1, 1, 1, fine, you can keep just 1. But when there is a change in direction, then there is an issue with that kind of averaging. The chain code may be normalized for rotation by taking the first difference, like a derivative, and adding 4 or 8 to negative differences depending on the first or second code. And rotation of a given contour by n times 90 degrees in the counterclockwise direction is achieved by adding a value of 2n to each code element, followed by integer division by 8, and addition of an odd number rotates the contour by a corresponding multiple of 45 degrees. So you can achieve rotation. The length of the contour may be computed, the perimeter, by taking the number of codes and multiplying by the step size in the first case. In the second case, for the odd codes, you need root 2 because you're making a diagonal step. There are a few other properties. You can achieve reduction, check for closure, check for multiple loops, and so on. So in some of our projects, when the radiologist drew contours of masses with, as I showed here, 8,000 points or so, a contour like that is very difficult to draw on a digital a display looking at the mammogram. You draw that using a tablet, but then sometimes there could be some small tremor in drawing, and the contour could sort of loop on itself. And we need to get rid of all of that and clean the contour before further analysis. So it is one closed loop. You don't want it backtracking and having these little protrusions or loops. So the Freeman chain code can facilitate checking for multiple loops and also get the area and so on. So here is an example. I have prepared a better illustration. I don't have it here. I can show you later on if you want. So assume that there is a real contour, something like that. If you were to use only horizontal and vertical movements starting from here, then the code is 0. The next point is this. Let me see. Instead of this, I do have the other one. Okay, this is the new edition. I did a different illustration. So this is the dashed line is the original contour on some piece of paper, and this is my grid I have superimposed. So I take that as the starting point, and in this case, this is the starting point here, this solid one. So from here I go clockwise. So it's 1, 1. So this point is approximated by this point. That point is approximated here on the grid. So the real contour is that shape. So if I use only these 4 directions, that's the closest approximation I get. So the code is this. From here, 1, 1, 1, 1, 1, 0, 1, 0, 3, 0, 0, 0, and so on. So that is the chain code. For the same contour, if I now allow the diagonal connections, I get a better representation. As you can see, the overlap between the solid line and the dashed line, which I was missing in the first case. As I started developing more and more illustrations, I learned all these tools a little better and better, graphic tools. So here, the same vertical is 2, not 1. So 2, 2, 2, and so on, and 1, 1. Now you have this approximated better. There is a diagonal here and there. So the diagonals give you a better matching of that shape. So that's the code. We'll skip this part. So given a contour that is complex with so many protrusions and incursions and excursions, spicules or lobules and so on, how do you break it into parts so that I can analyze each part and characterize each part? Segmentation of contours or breaking a contour into parts. You would want each part to be piecewise continuous, or break the entire contour into a set of piecewise continuous curves. For that, you locate the points of inflection. And if you consider this function f of x, let the contour be represented in this fxy format, and let these primes indicate the order of the derivative, single prime, double prime, triple prime for the first, second, third derivatives. A point of inflection on this function or curve in 1D is defined as the point where the second derivative changes its sign. And to obtain the second derivative, you require the function fx and f prime x to be continuous and differentiable. So there are some conditions required. And then for the point of inflection, these are the conditions. F double prime x is 0, f prime x is not 0, and f double prime should be 0, and f triple prime should not be 0, the product that is. So those define a point of inflection in the 1D curve. Now you extend it to 2D. I thought I fixed this. That should be bold. So if you have a contour capital C here, x and y, and a 2D contour now with n points, then the conditions are the first derivative cross the second derivative must be equal to 0. The first derivative cross the third derivative must not be equal to 0. And they turn to these equations in the partial derivatives in the x and y directions, similar to the 1D case. So solve these equations, you find points of inflection. The problem is contours drawn by hand or obtained by segmentation techniques have some artifacts. And those artifacts can give you some false points of inflection. You get too many points of inflection because the curve is jagged somewhere. So we take a derivative, xn plus 1 minus xn minus 1 divided by I, and then average that over a number of points along the contour. So we smoothen the contour by applying a low-pass or moving window filter along the contour, and then compute or determine these points of inflection. Olivier Minute from France came and did some project with me, and he wrote some of this code and developed the algorithm. The value of M, the moving window for filtering, is an issue. Number of inflection points detected as a function of the number of differences used was analyzed to determine the optimal number of points. After a certain amount of filtering, the number of inflection points detected did not change. So that's what we will take. So here are the points of inflection on a speculated tumor boundary as drawn by Dr. Desertel. Now there are some here they're almost straight, but still, if this is concave, curving inward, this has to be convex. There is a small curvature, so there is a little bit of waviness. So these points were detected. If you do more smoothing, it is possible to get rid of these excess points, but you may lose some real points of inflection by excessive smoothing. So we kept this. So filtering, beyond a certain amount of filtering, the number of points of inflection remained the same. If you don't filter, we were getting 1,000 points. With filtering, it reduced to how many? 58 points. The contour has a few thousand points. Now in between each of these, now you can say this is one piece, this is another piece, that is another piece. So what do you want to do? You could try to model each piece separately. You can't model the whole thing as one geometric shape. In one of our projects, we said we will take these points of inflection. We are breaking the contour into concave and convex parts, or incursions and excursions. This is incursion into the tumor. This is excursion, or going out of the tumor, protrusion. And Dr. Desertel gave us a very basic idea that if a mass or a tumor is benign, it is usually solid and has nearly a smooth round or oval shape. No concavity, and especially if there is a convexity, there must be a concavity. The whole thing is convex. There could be small artifacts. But if it is malignant and speculating, there is a protrusion, and there are multiple protrusions, and between protrusions there must be a concavity. So the presence of concavity is an indication of malignancy. So we said we will break the contour into these parts. The black parts are all done automatically. The black parts are concave. You measure the length of all the concave parts, you know the perimeter, add the rest, and get a measure of fractional concavity. How much of the contour is curving inward? And for this case, it is 0.47. We have superimposed the contour on the original image here. The contour was drawn by the radiologist. We couldn't get such an exact contour by any segmentation technique. We got some approximations. This is benign, what is called macrolobulated, 4 big lobules. It's not a perfect circle, so in between the lobules there will be small parts of concave segments. So concavity is 0.16. So that turned out to be a good discriminant variable or parameter. Polygonal modeling or approximation of contours has been around in the literature for some time. There are a few different algorithms, but we found limitations in many of these algorithms. Pavlidis has some, and Ventura and Chen have proposed some. And they applied this not only to closed contours, but also open contours like signals, ECG signals and so on, handwritten numerals. So you could approximate various contours, open or closed, by fitting polygons to parts. Now how do you get the parts is another question, but we did our partitioning as I showed just now. So in our work, a polygon is formed by using the points of inflection. Connect the points of inflection, but that's the initial step. And then you modify it iteratively. I'll just use the all of this I'll just show using this picture. So this set of points of inflection on that contour I showed earlier. Certainly this is not a good polygonal model. These are all straight lines. So the initial number of sites is 58. So now the algorithm says take one of the sides of the polygons and compare with the actual contour between those 2 points. If the distance between that line and the maximum distance between this line and the contour, which is maybe that, is more than some limit, 0.5 millimeters, 0.25, whatever you want, then you say that is not good. And you put another vertex of the polygon there where the distance is maximum. So the number of points is increased, the order of the polygon is increased. In this case, that distance is very small, you don't have to do anything. Here, that distance is large, so you would want another point there. So keep doing that, and iteratively. So you may put that, but even this may be large, so another point, and so on. And we haven't marked all the points here, but the straight line is there. There are 146 sides there. And that is a better approximation in terms of polygons, or one polygon, not polygons. So you see the actual contour and the sides of the polygon. Okay? So the iterative method converged within 3-4 iterations. Starting from 58, it reached that 140 something in 4 iterations. 1, 2, 3, 4, 5. Yeah, there that's the end. For a benign, the contour of a benign mass, the number of initial sites is 14. The number of sites after convergence is 36. You don't need that many. It's not as complicated as in the other case. So that is modeling using a polygon. Now, Minute said, well, why a polygon? Let's use parabolas. Now, polygon is also approximating the contour well, but you need so many segments or so many vertices. In parabolic modeling, we take each of those segments between points of inflection and fit a parabola. And use the parabola, go back here, this here also. So that is a parabola, this is a parabola, but they're all rotated and displaced wherever. The aim in this case, in the first case, was to approximate the contour fully, so that there is a mapping of the original contour to the polygonal model. In the case of the parabolic modeling, we didn't want reconstruction, we wanted feature extraction directly. So for each of those segments, you fit a parabola. But because they are rotated and shifted wherever around the contour, some processing was required. So consider a segment of the contour represented by xs, ys. S is the variable along the contour. The parabola is y equal to ax square in the transformed space capital X, capital Y. A controls the narrowness of the parabola. The larger the value of A, the narrower the parabola. In the case of, I mentioned that in the case of malignant tumors, we have narrow protrusions, narrow parabolas. In the case of benign masses that are macrolobulated, the lobules are big. So the value of A should be the opposite. Should be larger the value is narrower, so it should be smaller. So theta and the shift are the parameters required. So xs is capital Xs cos theta minus ys sin theta plus c, and ys is a similar function. So rotation and displacement, that's all. So you go through all of that, and then you get these equations for the parabola, and then you want to take the derivatives and solve for all of these equations, and finally you get 2a cos theta is that. So that's one equation. Then you get 2a cos theta is y double prime s. So you can solve for these parameters a and theta, and then you have the transformation. So you got the parameters of the parabola for each one of them. The problem is you need the derivatives, and again you need smoothing. You saw the original contour was fairly rough. There were little variations that are not important. So you need to get rid of them. So before taking the derivatives, you need to apply a smoothing filter or compute multiple derivatives and average. You smooth the signal and then contour and then take the derivative, or take the derivative and then filter the derivative values. So benign masses being oval or macrolobulated should have a small number of parabolic segments with small a. And larger standard deviation a for malignant tumors. There are multiple parabolas with various values. So they should be So we use these statistics of the parameters, and we got 76% accuracy with 54 contours. Our database only had 54 contours at that time. Later on, we expanded the database. So in this case, we didn't put the parabolas back. If you were to display there, just a bunch of parabolas. There's no need to plot them. We just wanted the parameter A. Theta is not important. It's just where it was located. And the displacement is not important. So there's only one parameter for each parabola. How big is it? And how many of them are there on the contour? And what is the standard deviation or variation of A around the contour? So very simple. Gave 76%. Now I'm quoting some results in some cases. It doesn't mean this is the end of it. This is one representation and one set of parameters. 76% is not good. So you want higher accuracy, bring more and more and more parameters from different perspectives. Not the same idea, but different ideas. So then, by combining them, as long as they are sort of independent in perspective and in the way they are computed, you will get better and better results, as I'll show later on. I'm showing one method at a time, but that doesn't mean one is good or adequate. When you have some contours or some extracted patterns, not necessarily contours, but some tree kind of a pattern, then you may not want all of the pixels, but simply a skeleton or a thinned down version of that to do further analysis. A skeleton is like the medial axis. There's a transform known as the medial axis transformation. So a skeleton of this would be just one line going through in the middle. A skeleton of this would be just the rim. But what is the skeleton of this? It's a thick object. So you will have the middle line, but then there are these variations in shape. So then the skeleton becomes a little bit more complicated, as you will see. Objects that are linear or oblong, or structures that are branching patterns like blood vessels, may be characterized well by their skeletons. You don't need all of the pixels. The skeleton could be obtained by what is known as the medial axis transform, or a thinning algorithm, or by morphological image processing. We are adding some morphological image processing techniques in the next edition of this book. The medial axis was proposed by Bloom, and it says the given image is to be binarized first, of course. You have detected the object. It's a binary image. So let those binary pattern pixels be denoted as B. Let C be the set of the contour pixels of B, and let Ci be an arbitrary contour point. So you want to remove all points that satisfy certain conditions. For each point B in that object, capital B, a point Ci is found such that the distance between the point B and Ci, D, B, Ci, is at its minimum. If a second point is found such that C equal D, B, C, K is equal to this, then B is a part of the skeleton of capital B. That is, you're in the middle. There are 2 points on both sides having equal but similar, we say, in practice. Otherwise, B is not part of the skeleton. So you have to find a line that's somewhere in the middle of that segment and do it for every pixel. There is a thinning algorithm from Gonzalez and Woods, and they have given references, and I have the references in the book. So if you have this pixel being processed and its 8 neighbors are numbered in this order, the other way, 2, 3, 4, 5, 6, 7, 8, 9. P1 is the center pixel. Then there are some conditions that are checked. They're all binary, 0, 1. So for a contour point P1 for deletion, the following must be met. The number of neighbors must be between 2 and 6. SP1 is the number of 0, 1 transitions in that sequence as you go around the neighbors must be equal to 1. The product of 2, 4, 6 and 4, 6, 8 must be equal to 0. That is these 2, 4, 6 and the other was 4, 6, 8. And similarly, similar patterns are checked in the next one. So if these conditions are met, you delete those pixels and then replace these conditions with 2, 4, 8, 2, 6, 8, which is 2, 4, that one, and check these conditions. And iterate. Delete those that satisfy this condition and keep iterating until there is nothing more to be done. It does not remove endpoints, does not break connectivity, and does not cause excessive erosion. That's the advantage. So this is the binarized image of a blood vessel pattern that was obtained in the ligament of a rabbit. Some of these projects were conducted in collaboration with orthopedic surgeons. And Dr. Bray was the principal clinical researcher in this project. And the interest, I mentioned collagen fibers. We will see both collagen fibers and blood vessel patterns in ligaments in this chapter and in the chapter 8. The story is that in ligaments, which are connective tissues across the knee joint, taking from one bone to the other, we have the medial collateral ligament and the cruciate ligaments and the the other side, another ligament here, the lateral collateral ligament. So these connect across bones and hold the bones together in the joint. So as we walk, the bones don't separate. These ligaments are made up of collagen fibers, and there is not much blood supply there. So that's why if a ligament is ripped or torn, healing is difficult. But in response to injury, if something happens and the ligament is torn, new blood vessels are formed to facilitate healing. And after healing is complete, those vessels disappear. So to study the healing of the ligament, Dr. Bray wanted to study the blood vessel pattern in normal ligaments and injured ligaments and ligaments that were recovering from rabbit models. And also, the collagen fibers that make up the ligament have an organized structure. I showed you some collagen fiber images with those nearly vertical fibers. Along the axis of the ligament, in the normal case, collagen fibers that are a few tens of nanometers in diameter are like strands of a rope. There will be some twisting over the length, change of orientation, but if you take a small section, they are mutually parallel lines along the length of the ligament. In the case of an injured ligament, when new collagen fibers are being formed by depositing collagen, that ordering doesn't exist. And the ordering comes a little later. It develops later over the course of a few weeks. So we wanted to study two things: collagen modeling, comparing normal organization, the parallel structure, with scar tissue where there is no structure, and recovering tissue where order returns slowly. That you will see in chapter 8. And blood vessels, there are more blood vessels in the periphery, or what's called the epiligament, on the outer surface of the ligament. But inside the ligament, the true ligament, there are not many blood vessels. In the normal case, they all run parallel to the ligament axis, long axis of the ligament. In the injured case, they are scattered with no direction, no preferred direction, and there are more of them. So here is one of those. Unfortunately, in these experiments, the rabbits have to be sacrificed. When you cause the injury, the rabbits are allowed to heal for a certain amount of time, and to extract the sample, the rabbit has to be sacrificed. Take the sample out. For the collagen fibers, the samples are treated in various ways described in the book and our papers, and they're either cut in cross-section or fractured, and electron microscopy is used to obtain those images I showed. Either the collagen fibers along their long axis, or a cross-section, those circular images I showed. In the case of blood vessels, black ink is injected into the ligament, and then it is allowed to spread into the ligament, and then the ligament is taken out, it is frozen, and then sectioned using a microtome. There was no microcomputed tomography, but these samples are very small, so even microcomputed tomography can't give us a 3D image. So the sample was sliced using a microtome, and pictures of this nature come up. Blood vessels have the black ink, so they show up. So that is the story, which we will see perhaps a little later, but I have told you the story now. Now we wanted to analyze the orientation distribution of the blood vessels. What is the thickness and what is the orientation? Obviously, there are blood vessels in different directions here. To do that, we did pinning and getting the skeleton. So this is what you have, skeleton. And at each point, we computed the thickness or the area, going back to this image, and then the angle, and obtain statistics of those that I'll show later. So here I just want to show the skeleton. Okay? We're going to 12:30, right? Okay. Now there are several shape factors that have been defined in the literature, and we came up with a few more, specifically for the analysis of calcifications and tumors in mammograms. So a shape factor encodes the nature or form of a contour. The nature of the contour to be encapsulated varies from one application to another. What is it that you want to represent in the shape factor? We will see a few examples. Regardless of the application or what kind of shape factor you get, there are a few requirements. There is a term that is used, they say invariant shape factors. But that's not specific or clear enough. Invariant to what? Invariant to what kind of transformation you have to say. If they're invariant to everything, then they're useless because they're not varying between benign and malignant. So they must vary between benign and malignant and class A, B, C, D, whatever you have. But they should be invariant to shift in spatial position. That's very easy. Whether it is here or there, you should get the same number. Rotation, that's also a requirement. Scaling, whether it is that big or this big, it should be the same. For all squares of any size, the number should be the same. All circles should be the same. That's good. Invariance to reflection may be desirable in some applications, not always. If you do character recognition, you don't want invariance to reflection because we have P and Q and B and P and so on that are reflections of one another. So in character recognition, you don't want invariance to reflection. In mammography, tumors and calcifications, yeah, maybe. But we could reflect the image before you do that. It doesn't matter. So shape factors that meet these criteria can effectively and efficiently represent contours for pattern classification. These are some basic requirements. A very basic shape analysis technique is to fit a rectangle or a circle. So if you fit a circle or fit an ellipse, then you can measure some very basic parameters. Circle, you can say, well, that's the approximate diameter, square the approximate width, but better, fit a rectangle. If you fit a rectangle to this, you have the sort of height and width. The ratio, it'll tell you if it is oblong. Is it square or oblong? If you fit an ellipse, it'll give you an eccentricity ratio. How far is it from a circle? That's also a measure of being oblong. So eccentricity or elongation can be measured by using a bounding rectangle or a bounding ellipse. That can be done fairly easily, and you can do some of this using the Fourier coefficients that we will see later. Compactness is a very popular method. It's been around for a few years. The basic initial definition given in the literature was P squared over A. P is perimeter, square it, divide by area of the area contained within the contour, and that gives you a number. Area cannot be zero. If area is zero, it's infinite, but if area is zero, there is no contour, no object. It's just a point, so that doesn't matter. But the problem is this is unbounded. As P increases and area is small, it becomes very large. So you don't have a fixed dynamic range for this. The smaller the area contained by a contour of a given length, the larger will be the value of the compactness. So you can take a piece of string of a certain length, and you can form various shapes. The longer the shape for the same length of the contour, longer in the sense, if you just fold the string in half, there is not much area, so it is not an efficient representation of area. If you want maximal area to be contained within that string of a fixed length, then you should make a circle. You get maximal contained area. Now it is possible to normalize this and turn it around A over P square. So if P increases, then compactness reduces. It is not compact. That is, area is small, perimeter is large, it is not compact, it's being stretched. And if you put 4 pi and take 1 minus that, then you have a number between 0 and 1. And if you take a circle, the value will be 0. So a circle is a perfect shape, the most compact shape, the value will be 0. The maximum is 1. So that's a nice normalized range that we have used. It is obviously invariant to shift, scaling, rotation, reflection. All of those conditions are met. So if you have a circle, you get this 12.57, square 16, rectangle 18. You stretch the rectangle more, 25, very sharp triangle 41, and so on. If you take the normalized one, circle has 0, and then 0.2, 3, 0.5, 0.7, increasing. Now, increasing roughness is as you judge it, and you and she may judge it differently. You say something, I say something else. Which one is sharper, or which one is more rough? It's a bit hard to say. Circle is not rough, fine, but between these two, it becomes a bit of a personal preference. So in some cases, you may want to get all your objects sorted out by a number of observers and average the ranking and say that is the average ranking given by a number of human observers. And then check if this agrees. The feature that you have computed agrees, correlates well with that ranking. So my student Liang Shen, for his master's work, he did some work with generating some basic shapes digitally, and also by taking black paper and cutting like children do in kindergarten. We were making fun of him. Prepared those and then computed. Now these were digitized, so it's not digitally generated. No, this is digitally generated, but different circles, only the shape is changing, the radius is changing, the squares, side is changing, and rotation. Rectangles, different aspect ratio and orientation, different types of triangles. And we computed a whole bunch of shape factors and showed how all the circles have 14 point something, all the squares have 15 point something, close to 16. All the rectangles have 17 point something. The isosceles triangles have 22, and the right angle triangles have about 27, plus or minus a little bit. And a few other factors that we will see later on. And then he also did this with paper, and then scanned, or digitized, I should say, with a camera. And then he ranked these as shown, 1, 2, and so on. This is like a speculated tumor, and put that as 12. But some of you may rank these in a different way. And for these, compactness is going that way, and not exactly in the way he ordered. Number 7 is 0.22. It's going back. It's not, that sequence doesn't agree with this sequence. In some other, depending on which shape factor you compute, that ordering may vary. So which one do you want to choose is a question. You may put all of them together. Moments of several types have been defined in the literature. Moments of images, moments of PDFs we have seen. Moments of PDFs have mean, standard deviation or variance, and skewness, kurtosis, and all those are higher order moments. But you can also take moments of images. You can imagine the image to be like a plate where each point has a different weight depending on how thick it is. So non-uniform thickness plate where the thickness depends on the gray level. And then where is the centroid? The point where you can balance it, that's the centroid, if you can balance it. If the centroid is within the object, if there is no concavity, then you will be able to find a centroid that is within the object. You can also imagine this as a beam with some load applied, and there is a bending moment. There is a beam supported here, and on the beam you put some weights, and you take moments, the weight times the distance from the point of support. So here, xy are the coordinates, and fxy is the image. So x to the power of p, y to the power of q, fxy, integrated over x and y. That is the order pq of the moment over the entire space of the image. Plus minus infinity, but over the space of the image. So there is a uniqueness theorem that says if fxy is piecewise continuous and has non-zero values only in a finite part of the xy plane, then all moments of all orders exist, and that moment sequence is uniquely determined by the image, and the moments determine the image. But we are not interested in reconstructing the image from the moments. We will compute only a few moments and use them in pattern classification as features. So that is a theoretical nicety, but not very important. If you centralize this factor with respect to the centroid, x bar, y bar, which are the first moment m10 divided by m00, m01 divided by m00, then you get the central moments, like the variance. How is the distribution of the weight in this plate of the image with respect to its center of mass? The same thing, these are called mu pq, x minus x bar, y minus y bar to the power of p and q, fxy. So it's like a PDF. Essentially, you're treating the image fxy as a PDF. There is no normalization here, but normalization comes here. So the gray levels of the pixels provide weights for the moments, and you have the coordinates to the power of p and q. Digital image, the same thing, just replace integral by summation. If you compute the moments for a contour, if you have segmented an object like a tumor, there are a few different possibilities. You could say all the points inside the contour are equal to 1 and outside 0. Or you may say, I use only the contour points. I don't care what is inside. So FMN will be defined according to that. If it is the original image, that's the gray level value. If it is a contour that is binary, what do you do with the points inside as compared to the outside and on the contour? So you have some options there. Normally you would just use the contour pixels. The pixels within the contour will be set to 0 and outside too. So there are a number of these relationships. There was a paper by Hu, H-U, and it was a short communication paper, but it has a very large number of citations, very popular, and many people have referred to that. So Hu defined a number of these moments and their relationships. Again, you don't have to remember these. Some of the basic ones you can find, you can determine easily, but the others, let's not worry about that. Normalization is achieved by dividing the moments by mu 0, 0 to the power of gamma, where gamma is p plus q over 2 plus 1. So then they are written as mu pq over mu 0, 0 to the power of gamma. I said earlier that those were not normalized. This normalizes them. And then who defined these moments? I won't read them. You don't need to memorize them. There's a bunch of moments based on second and third order central moments. 2002 second order and 3012, those are third order. P plus Q is 3 here. And more of these, M1 to M7. These are very popular in pattern recognition. We have used them too. They're said to be invariant to shift scaling rotation and useful for pattern analysis, but we found some limitations in analysis of breast tumors and calcifications. I'll show those later on. If you go back to that big table I showed, you will see how they vary, and the moments that we designed don't vary as much. So moments of distances to the centroid is another possibility. We earlier saw the distance dn, square root of xn square plus yn square, distance. So you can take those values and treat them as a distribution and take moments of those. So when a region is represented using only its contour, then do you want to use the contour pixels? Do you want to use the distance? The distance is the signature, like a 1D signal. So statistics of those values. Now we plotted them as a signal by going around the contour once. But there is no, you can just take them as a bunch of numbers and compute statistics. All those radial distance measures. That's what you do here. The distances from the center of a circle to its contour points are all equal to the radius. So the variance is 0. The average value is the radius. So the moments, central moments are all 0. For rough shapes, the distances will vary considerably. So variance and higher order moments of those distance values could be expected to be useful in pattern classification. So it is just this dn to the power of p. For the pth central moment, dn minus m1. M1 is the first moment, which is just the average, to the power of p. That is the pth central moment. Second order moment is the variance. You can normalize, but normalization, there are a few different possibilities. What should be the denominator for normalization of the higher order moments? The pth order moment, dn to the power of p, divided by what? The Ks statistic, Kolmogorov-Smirnov statistics, will use the variance to the appropriate power. This is the variance, dn minus m1 square. That's of order 2. This is of order p. So raise this to the power of p over 2. So this also is of the power p, that is power p for normalization. And then the same for centralized. dn minus m1, this is the central moment. The denominator is the same. Variance. This is the variance to the power of p over 2 for the pth order moment. This was proposed by Gupta and Srinath, and they showed that these are useful in classification of airplane shapes and a few other shapes. But we found some difficulty with this, and we changed the normalization. The main difficulty here is high order moments are sensitive to noise. Noise meaning the contour is not perfect. When you perform segmentation or you try to draw a contour, there'll be some small tremor, especially on high resolution images with pixel size of a few micrometers. Then you need to take care of that, pre-filter, or don't go to moments of very high order. So Gupta and Srinath, they used 4 normalized low order moments. So they said F1 is the square root of the second moment, that's like the variance, divided by M1. That's like coefficient of variation. And M3 over this is like skewness, and that's like kurtosis. Standard statistics. Okay. So Liangshan, my student, he worked on this. We tried to incorporate, we had our own shape factors, but for the sake of comparative analysis and to see if combining our shape factors with others would help, we computed some of these well-known shape factors too, whose moments and those of Gupta and Srinath. But we found that the variations in F2 and F3 for different shape complexity was very small and did not show a good progression from smooth shape to rough shape as we or the user judged it to be. F2 was observed to vary significantly for the same geometric shape but with scaling and rotation, those circles and squares of different size that I showed earlier. So Liang modified F2 and F3, changed the normalization, so all of them are normalized by M1 now instead of the variance to the power of P over 2. So, and we took the numerator, this is the 4th order moment, we took the 4th root of that. So the dimensions must be the same. So instead of taking variance here and raising it to the half of the power of the numerator, we use mean here and take the appropriate 1/p root of that so that dimension agrees. And we found this to be better and we took the difference between them. So we call this MF, F3 minus F1 according to our definition. So let me go back to that. We found MF to be relatively constant in each of these sections and then increasing monotonically except for these two. Is isosceles triangle sharper than right angled? I don't know. They are both sharp. And for these objects, MF, let's see. No, it's not exactly that, but it's increasing. This is a problem, number 7. It's not in that order. We got the order we wanted using the Fourier descriptors, monotonically increasing. Compactness and moment factors did not increase monotonically. Mostly so. No, here's going back. This is 1, 4, 7, 8, 9. Yeah, this is increasing monotonically. But that's ranking of the shapes by one person. Okay, let's go back here. Yeah. There was another method proposed to take lengths of chords and use them as variables in computing statistics, called chord length statistics. A chord length measure Lk is defined as the length of the line segment that links a pair of contour points, normalized by the length of the longest chord. So if this is your shape, from every point on the contour, you draw lines to every other point and find those distances. They are the chord lengths. Now there is some duplication. You can go this way and come back the same way. So eliminate the duplicates. So all of these lines are taken. Their lengths are measured. Duplicates are removed. And then you take statistics. The same statistics, mean variance, standard deviation, skewness, kurtosis and all that. And that was proposed in the literature. These are just the KS statistics I mentioned earlier, so I won't go through the equations. Okay? Any questions so far?
In the earlier lecture, we were looking at these microscopic different shapes. Like, I was thinking tumors of various shapes. But when it comes to the medical aspect of that, for example, if you want to remove the tumor out of that much of a detailed thing that may not come to the practicality. Like,
True.
unless otherwise it is taken from just shape perspective, shape analysis, and a very,
True.
very general context.
True. Yeah, the comment is, will the shape of the tumor matter in surgical resection of the tumor? Quite likely, a much larger part of the breast or whichever part of the body it is will be taken out to take some surrounding tissue out without affecting major blood vessels and organs, because the tumor could have spread. So no, the contour that we obtain or drawn by the radiologist, in practice the radiologist never draws the contour of a tumor. The radiologist simply says there is a tumor there, and then a biopsy is done by putting a needle, and ultrasound is used to make sure the needle goes in the right place into the tumor to confirm benign or malignant. And then some treatment is applied, could be chemotherapy, radiation therapy. The resection of that part may not be done unless it cannot be addressed by radiation or chemotherapy. Full mastectomy may not be done right away, but segments of the breast may be removed. And there are some other considerations into how they do that. I can't go into the details of that, but segments of the breast are removed, if not the entire breast. You don't go into just the tumor shape there. This is for analysis to assist in the diagnostic interpretation of mammograms, especially in a screening situation where there are hundreds, maybe thousands of mammograms taken, and every day the radiologist will sit there and in one session of 2 hours may go through 100, 200 patients' mammograms, and each patient or subject will have 2 images per breast, so 4 images from the current session, 4 from the previous, and 4 from the one before that, if the person has been in the screening program for more than 4 years. So 12 images. So look at that, and within a minute or 30 seconds, sometimes, come up with a diagnosis, no change, go home, don't come back in 2 years, or something has happened, come back for more examination. That's all. But this is more of a theoretical exercise, all right. But if one were to ask, detect tumors and classify them, this helps. For further management, no. And as Dr. Desertel has said, if there are more than 10 calcifications in 1 centimeter square, we'll call it malignant. Whether you detect 10 or 200, it doesn't matter. And similarly, if it is a spiculated tumor with 200 spicules, if you detect 20 spicules, it is spiculated. 200 spiculated, it doesn't matter anymore. Call it malignant, you're done. It doesn't mean that we should sacrifice the accuracy of our method. We should try to be as accurate and precise as possible, but the diagnostic interpretation may not change if I lose 2 spicules out of 50. But I don't want to do that. I don't want to design my algorithm to fail like that. But that's for classification only, diagnostic classification. A radiologist will do that just by looking at it. Now, in a practical situation in Canada, we did all this and published and said, okay, we will develop a package, we will give you, in the screening program, we will give you our programs, and previously it had to be filmed. We said we'll put a monitor. Now everybody uses computer displays. So another display, the original and processed. But the screening program is controlled by the cancer board. There is a very specific protocol. A number of women come there, and it's not to be taken lightly. It's a very serious matter, and I can't just go and stick my computer there. There's a protocol. I can't change that. And then they said, well, all of this is not for screening, but diagnostic application. And in a diagnostic situation, the radiologist has more time. There is already suspicion, and the radiologist will look at multiple things and will spend more time on each case, and will get ultrasound, MR, everything. There they said, we will consider your input. Screening, they wouldn't let us touch anything. The screening films that we got to our lab for digitization, we were not allowed to even touch it. As a member from the screening program came to the lab, my student set up the digitization system, and she did all the scanning and took everything back and deposited. We couldn't even see that. So there are very strict protocols, and they're hard to change. Now, CAD systems that have been licensed by the US FDA, they have passed through all those protocols and tests. They have been put into the screening program. So, but even then, the radiologist is not allowed to look at the output of the CAD system. First, the radiologist has to look at the images, dictate or record the diagnosis, and then look at the CAD system and say, well, I'm not changing it. Or say, well, I looked at the CAD system output now, and something else appears, I'm going to change. So CAD is number 2, second opinion. So, yeah, all of this, we did decades of work on this. So people often ask me, did you do something useful? Yeah, we added to the knowledge base. Did you put your software in a screening situation? No. And that's not my job. I'm not going to sell this. And I'm not going to prepare a module that can be put there. I'm a researcher. So some business person will have to invest millions of dollars to take this, test it over and over again, and get US FDA approval. So the story is more complex than what one can imagine. A lot more complex. Okay, we still have a few minutes. Let's look at Fourier descriptors. We saw the Fourier transform, the DFT and everything. Fourier series you would have seen in your first year calculus or wherever. So you know very well that if you have a periodic signal, you can represent that signal using the Fourier series, which are complex exponential functions or sines and cosine functions at integral multiples of the fundamental frequency, or harmonics of the fundamental frequency. But then you go to infinity. You have a large number of those coefficients. Many of the high order coefficients may be very small, so you stop at some point. So here we represent the contour as a complex variable. X and yn are the coordinates in the x and y locations of a discretized contour 0 to n minus 1. The complex sequence Zn is xn plus jyn. So z is a complex quantity I showed earlier on that contour. We saw the distance dn, but every contour point now is this Zn. It is periodic. Go around a circle, you get the same thing. The magnitude of Zn is the same as dn, that signature of that distance we saw. The Fourier series now, known as Fourier descriptors, is expressed as capital Zk, Zn exponential minus j2 pi over n nk. DFT, that's all. Endpoint, DFT. You have endpoints in the input, you have endpoints in the output. It is DFT, but the interpretation of the coefficients is that these are Fourier series coefficients because of periodicity. And they're called Fourier descriptors. But we let k go minus n over 2 to plus n over 2 minus 1. And because this is a complex quantity, Zn is complex, there is no conjugate symmetry. Z minus 1 is not equal to Z1 in magnitude, like in real signals. in general. So the frequency index k is interpreted as the index of the harmonics of a fundamental frequency, having one sinusoid or two, one period of a sinusoid or two periods and three, and so on around the contour. The inverse is given by Zn, k going minus n over 2 to plus n over 2. So here we said 0 to n minus 1, going once around the contour. But k is indexed this way, and the inverse. So from the Fourier descriptors, you can go back. This is exponential plus j2 pi. So it's reversible. So just a DFT. The interpretation is different. The complex coefficients zk are known as the Fourier descriptors of that contour. Zk is a two-sided complex spectrum with folding or shifting of the DFT array. The index will run minus n over 2 to plus n over 2 minus 1. The DFT may give you 0 to n minus 1, but you have to index properly. So the DFT may give you index like this, but rearrange it. So k represents the harmonic number. The fundamental frequency k equal to 1 represents a sinusoid in x and y, and differing from spectra of real signals, Zk does not have conjugate symmetry, because conjugate symmetry is for real signals. If xn or zn, whatever is real, then there is conjugate symmetry in the Fourier transform. Now, it is not so. The zero frequency or DC coefficient Z0 represents the center of mass, centroid. Z0, the exponential goes away. It is just sum of Zn, average, and x and y separate, so x bar, y bar. The fundamental frequency coefficient Z1 and Z minus 1 represents, each one of them represents a circle. So you get two circles, one for Z1 and for Z minus 1. If you use both of them, Z minus 1, Z1, you get an ellipse. Z0 is the centroid where you put the ellipse. But if you don't care where you draw it, two coordinates will give you an ellipse. One will give you a circle, Z1 and Z minus 1. High order Fourier descriptors or higher order will represent fine details or rapid excursions of the contour. In 1D signal processing, we talk about phase shift or extra linear phase factor with a shift of the time signal. Here, we also have rotation. Rotation of a contour by angle theta may be expressed as Z1n, the new contour is the 1 hour? 1 hour, 1:30. Then we will continue. See you at 1:30. Thank you. 3:30 to 2:45 or 3?
3.
3. And then 3:30 to 4:30.
3:30. 3 to 3:30 is the tea break.
Yeah, 3:30 to 4:30. We close at 4:30. Okay. Well, welcome back after lunch. I have never tasted baby corn paisam. That was something new. That's what he said.
Something else today.
Huh?
That is something else probably. I don't. It's not baby corn.
I asked him. He said baby corn. Anyway, we looked at Fourier descriptors. Fourier descriptors will have a number of values, as many values as in this given contour, and coefficients complex. But of course, the input is also complex. So there is no data reduction, and we have that many coefficients. If you simply pump all of them in, there is no point into pattern classification. So it will be good to derive a few features or measures using the Fourier descriptors, and we will talk about one of them. Liang Shen, who did his MSc and PhD with me, developed a Fourier descriptor-based shape factor. First, set Z0 to 0, and the descriptors are independent of position. Z0 is just a centroid, so we don't care where it is. Each coefficient is divided by Z1 to normalize for size, but that also takes away the phase. Z1 is complex, so if you divide by that, the phase is also the phase of that is removed from the phase of the rest of the components. So the magnitudes of the Fourier descriptors are independent of position, size, orientation, starting point of the contour after this, if we take the magnitude. The orientation and starting point affect only the phase of the Fourier descriptors. So by dividing by Z1, we achieve some more convenient properties. So the normalized Fourier descriptors are the Z0 k, 0 for k equal to 0, Zk over Z1. So for this, the points of the contour must be indexed 0 to n-1 in the counterclockwise order. In the opposite case, you should use Z-1. Contours with sharp excursions possess more high frequency energy than smooth contours. I showed that. Similar to signals. More rapid variations, more high frequency energy. Applying a weighting factor that increases with frequency leads to unbounded values. So when we take moments, we multiply with a weighting factor, typically increasing, and more high frequency will say, well, put a weighting factor that is increasing with frequency. But then it is hard to normalize that, because increasing weights may lead to very large values if the high frequency contents become very large. So instead, we reversed it. Z0 k over modulus of k, and sum over all coefficients, normalized by sum of all the Z0 k, normalized Fourier coefficient values, and 1 minus that, and we call this the Fourier descriptor, Fourier descriptor based shape factor, and this is limited to 0 to 1. So we wanted to have a normalized value. It is invariant to translation, rotation, starting point, and contour size because of the other normalization already done. Increases as the object shape becomes more complex and rough within the range 0 to 1. So it is in a way low pass filtering here, and then normalizing, and 1 minus that. So 1 minus low pass, it's not exactly high pass, but it just gives you the opposite sense. If you were to multiply by k, then you'll be sensitive to noise, and we didn't want that. So it's a bit strange, but you will see how it works. I'll go back and show that table again with the shapes later. Fractional concavity I already mentioned, so I'll skip this. I showed that picture earlier. So let's look at another feature that one of my students, Naga Mudigonda, he developed for his part of his PhD work. Analysis of spicularity. We said malignant tumors have these spicules. The longer the spicule and narrower the spicule, the stronger the indication of malignancy. Broad, they're not spicules, but macro lobulated contours, if you want to call that a spicule, they won't be long. The excursion out of the main part of the object, the mass, will be short, and this angle, if you want to measure that, will be broad. So narrow spicules having narrow angle at the vertex and long spicule length indicate malignancy or higher probability of malignancy. So we proposed a speculation index to characterize this property, which was described by the radiologist. I'll skip all this. You can read this later. I'll show the picture, and that is easier. And we'll go back to some details if needed. So here is that malignant tumor again, and we have a spicule here between points of inflection. The plus marks are points of inflection. These are additional vertices of the polygonal model. So if you consider this spicule, the angle contained here is 36 degrees. But to measure the angle, we need to make put some rules here, do some processing, because it's not just two lines. There's 1, 2, 3, 4, 5 segments. So which angle do you take? So that is another question that comes up. In the case of this, which is not exactly a spicule, the angle, internal angle here is 170 degrees. So that's almost a straight line. So then we will put them all as spicules because we don't know which one. We could reject some of these, but we said, well, if the angle is so large, the weight will be low. But some of these are a bit hard to characterize. We got 108 degrees, and this is the average angle computed was 94 degrees. So there is an algorithm we developed for to obtain the angle in an average sense, which is like this. If a spicule, or if a part of a contour between 2 points of inflection, if that is a spicule, and there are no other points of no other vertices of the polygon, there are only 2 sides and 1 angle, no issue. That's easy. You just take that angle. But if you have 2 points of inflection, and in between there are other vertices of the polygonal model, then there are so many angles. If you have 5 sides, there are 4 angles, internal angles. So which angle do you take? So we said, well, we will compute a threshold by averaging all the internal angles. And those angles that are less than the threshold will be kept, and we will average them. The other angles are rejected. The length of the spicule is putting all of them together. Length is not a problem. Here also length, you just add up all the lengths of those sides of the polygon. This could be modified. Because we're averaging, we're getting some numbers that are large. There are several angles that could pass this threshold test. So you may define it to be something else if you want to avoid this smoothing of some kind. Anyway, we get all these angles, and it's all described there. We don't have to go through that. I have described using this figure. Then, if Sn and theta n are the length and angle of spicules, and there are n spicules, then we defined the speculation index as 1 plus cosine of theta n Sn. And if the angle is very small, the value of cos will be large. And we are adding 1 as a bias, because the angle could be more than 90 degrees. So we are raising the cosine by adding 1. And then multiplying by the spicule length, normalized by the total of the spicule length or the boundary of the whole contour. So let me show some results. That's simply the procedure. I think the Fourier factor, I already showed the Fourier factor in that table. I'll go back and show that. The Fourier factor, Fourier descriptor-based factor, agrees with this ranking that Liang had put in: 0.14, 17, 18, 19, 24, 25, 30, 36, 42. In that, this one. As I said, you may rank order these in a different way based on your perception of sharpness or complexity of some manner. Okay? The other compactness and moment-based factors did not give a monotonically increasing sequence of numbers for this set of objects. Is this correct? We could discuss that, but there is a sequence here. Okay. Liang Shen also did shape analysis of calcifications. I showed you a method to detect calcifications earlier. And then we measured statistics in terms of the density, and also we got a number of shape factors. Malignant calcifications tend to be rougher in shape than benign calcifications that have smooth contours. So here we have 143 calcifications, 79 malignant and 64 benign. The benigns are these circles, the malignants are these plus marks. Compactness, normalized CF. This is the Fourier factor, increasing that way. This is the moment factor. So there is good separation here. Compactness itself is doing very well, surprisingly. Sometimes as engineers and scientists we say, okay, so something more sophisticated and equations that look well, we go in a certain direction. We think that we are developing something fantastic or something original and novel and complicated, not too simple. But the simple measure of compactness has worked very well. The moment-based factor has worked well. The Fourier factor has worked well. In fact, the Fourier factor at one of our contacts, I don't remember which university, I think they were in Boston at that time. So they asked for this code and we gave the Fourier factor, and in their work that turned out to be the best shape factor in the analysis of tumors. So the Fourier factor has worked well in other applications in breast cancer detection. So separability of these clusters, malignant versus benign, is what we are looking for. To analyze this, you need pattern classification. That is the last chapter in the book. In that we have given some results of pattern classification using different methods. So here all I want to show is how these can achieve separation of these samples. Different pattern classification methods will give you different accuracy measures. We have used neural networks and we got nearly 100% accuracy with this data set. So another way to represent the features is in terms of mean and standard deviation. We didn't mark outliers. These box plots, one could also mark outliers. Benign and mean for malignant, and this is the standard deviation bar. So there is good separation. Fourier factor, benign, malignant. Again, there is good separation. Compactness, the best perhaps. So the simple measure of compactness is doing very well. And even with the standard deviation taken into account, there is substantial separation between the two clusters. Okay. These are not bad, they're working, but do we need these on top of that? No, not for this data set. But if you get a much larger data set from other mammograms, other patients, other subjects, perhaps you will need more features. So based on this one study, we cannot say this is the best and throw the others out. Shape analysis of breast masses and tumors, we had multiple data sets from the MAS database on which Dr. Desertel drew the contours and we obtained the shape factors. We did not analyze the shape factors from our mass detection algorithms. We just showed what you can detect and the accuracy of detection. We didn't use them in shape analysis. Instead, Dr. Desertel, our radiologist, had drawn these contours on the mammograms. So we took those and did shape analysis, taking these to be accurate. So we got one data set from the MAS database, which is this, and we got another database from the Foothills Hospital in Calgary, and later on we got another database of digital mammograms from Italy. So we did multiple tests. I won't show all of them. Here is one, and B is benign, M is malignant by biopsy. So that is the ground truth. And you can see most of the benign ones are almost round and oval. Some benign ones have a couple of spicules. Some malignant ones don't have spicules, but they are microlobulated. There is one benign that is coming at the end of this. This is rank ordered by the feature CF, compactness normalized, fractional concavity, speculation index. Those are the three features combined. Rank ordering, most of the benigns are there, most of the malignants are there, but there is some mixing. There are some benign masses with some speculation. Dr. Desertel questioned that this is the MAS database from the UK. He said he questioned this, whether they are really benign. But we don't have access to any more information than just the mammogram and the label.
The majority of the malignants have speculations.
Yes, yes. So speculation index, malignants higher. Compactness, malignants higher. Fractional concavity, malignants higher. Benigns are here, but some benigns have gone there. For this data set, only 54 cases. You need hundreds of them before you can conclusively say that one is better than the other. We have another data set. In some of our other papers, we have added more after this was published. So I don't have all of that here. If you are interested, I can send you some of our research publications with larger data sets and cross-validation. You train on this data set, test on the other one, try various feature selection processes, try various pattern classification methods. We have some other papers. So when you compute a number of features, suppose you compute 10 features. Here I'm showing 3. It's convenient to plot. If I have 10, I can't plot. Are they really mutually independent in the sense, are they giving you different information, or are they simply correlated? So you need a feature selection method to say, I have computed 10 features, but 3 of them are perhaps highly correlated with a few others, so only perhaps 7 of them are useful, or maybe only 4 of them are useful. A feature selection method will check for such correlation amongst the features you have developed, given the classification knowledge, and then you can reduce the data set at the size of the feature vector. Otherwise, your pattern classification algorithm may not work efficiently. The higher dimension may cause problems in pattern classification. And then there are so many pattern classification methods that depend upon the distribution. Are these Gaussian distributed? Are they multivariate Gaussian? What is the separability? So the result that you get depends upon the subsequent methods you apply. And if you have a big neural network with many layers, you will get 100%. With more training, more indentations in the contour, it depends on how you perceive the details. And if you're using a digital image processing method to get the contour, noise will affect the resolution and quality of the contour. In clinical practice, it is not common to draw the contours of tumors and organs. Radiologists don't do that in clinical practice. So one could say they don't have experience in doing that, but instead of that, we will say, well, that is not what they normally do. And if you ask them to do it, yes, after drawing some of them, they can do In many of our studies, radiologists have drawn contours of calcifications and masses, tumors, and various parts of the body. I'll show you in landmarking. But that is not what is done in clinical practice. Malignant tumors typically exhibit poor definitions of their margins. I've shown you some. So where do you draw the boundary? It is difficult. So identification and drawing of their contours is difficult either manually or by computer methods. You will only get approximate contours. So hand-drawn and computer-detected contours may contain imperfections and artifacts. So you may need to filter them. And there could be significant variations between contours drawn by different individuals and the same individual over time. But you won't find 10 radiologists to draw the contours of 1,000 mammograms 10 times each. It's impossible, although some reviewers may ask you to get such data. It's not possible. It should also be recognized that the contour of a 3D entity, such as a tumor, as it appears on a 2D image, such as a mammogram where the breast is compressed and you get a projection, a radiographic shadow, 2D of a 3D object, depends upon imaging parameters and projection geometry. You take it this way or that way or this way, the shape will be different. So a spiculated tumor, if it has spicules only in certain directions, they could all get integrated along the path of propagation of the X-rays, and you may not see anything in the image. Unlikely, but some of these spicules at least may disappear in the process of obtaining a 2D projection of a 3D body. And in some projects we have said, well, let's get the 3D data set and do the same thing in 3D. And I thought, well, doing in 3D may help and give us better results, but in some projects we got poorer results, and there are a few reasons there. In CT and other modalities of imaging, at least previously, the resolution between slices was not good. You could get high resolution in a plane, but not between planes. So 3D representation did not have isotropic resolution. The new scanners do. Most new CT scanners give you at least 1 millimeter, some of them may be even better, in all 3 dimensions. But then, are there spicules in all 3D? We don't know. It is very difficult for a radiologist to confirm that if the tumor really has spicules in all 3D. Radiologists have viewed the images only in 2D, the mammograms. So, in some cases, the 3D analysis did not give us any better result. That was a bit of a surprise, but it all depends on many factors of imaging and data acquisition and what really exists in 3D versus what has been seen in 2D and documented.
In phantom modeling and phantom to do in 3D anyway, it's a 3D, right? Speculations are there.
Yeah. We could do tests with phantoms. We have done with nuclear medicine. I showed a simple phantom. We had other phantoms of the ventricle, and we could insert what would behave as a tumor or what would behave as a blockage. But that is specifically for nuclear medicine imaging. There are mammographic phantoms too, but they are 2D. So we have 3D phantoms. But to create a phantom with spicules and so on is not so easy. So contours of biological entities such as tumors present overlap in their characteristics between categories. Benign and malignant, we saw they overlap depending upon the database and how accurately they were classified by the radiologist or the pathologist. Those categorizations, benign and malignant, were done by the pathologist in biopsy. Now the radiologist could go wrong. They may have 95% accuracy, let's say. Pathologists could also possibly go wrong. There have been situations where pathologists have not done a good job. Are they 100%? No. And how about the sample acquired in biopsy? If the needle is not put in the correct place, you may draw a normal tissue sample out and miss the tumor, or the sample taken may not demonstrate the presence of cancer. So the pathologist, if correct, will say benign. So there are possibilities of other stages of this analysis going wrong. So when we put a data set together like this, there could be errors in some other place also. What is important is we need to include other measures representing other image characteristics such as texture, gradient, and so on that should complement shape. Shape is only one thing, one aspect of this analysis. It is not the end of the story. Okay? That is the end of this chapter. It's a small chapter. Any questions on this shape analysis?
When we use deep learning kind of methods, we need the delineation by the experts and the radiologists. Anyway, radiologists, they have their own personal or subjective kind of thing, as you said. But we can automate that also using these type of fields. That may be used as a kind of a ground truth.
Automate to what? Detection?
Instead of radiologist delineating that, you can use some kind of a descriptors like this, where it gives a good result probably. So that can be used as a ground truth for the deep learning.
Yeah. We can use results of segmentation using multiple methods and then let the radiologist choose which one is the best and mark that as the ground truth. Is that what you meant? Yeah. Instead of actually drawing the...
For delineating everything is too time consuming and too tedious process.
Yeah.
So...
Yeah, with the Dennis Guglielmo, we also developed some graphical user interfaces, GUIs, so where the initial segmentation result is displayed with the mammogram and tools were provided to manipulate the contour. So to ask the radiologist to draw the entire contour may be difficult, or it may be difficult or too time consuming or too much effort and not worthwhile. But if you give an initial segmentation by one of the methods we will see later on for detection of tumors, or you saw the fuzzy set and all that, then you may say, well, could you please modify this? Just pull and push a few and fit Bezier or spline curves, and you can do that even in some basic software. Adjust, and then you can generate such ground truth, not completely drawn by the radiologist, but corrected, automatically detected contours, corrected and accepted or authenticated by the radiologist. Any other comment? Yeah?
So, going back to the stipulated contours, so were there instances where, the regions were not appropriately identified? Like, your approach was, purely, classical, like classical approach. So when identifying those, maybe like the tumors or something, so must it always fit? Because all examples you showed, it was like the approach was, efficient. Like, now were there instances where it didn't fit? Like,
Yes. I will show you some in chapter 8. Again, we have another method for detection of tumors, where I'll show where the methods worked and where they failed. In fact, right at the beginning, I showed that one picture, which is the cover illustration of the book, where the contour obtained by the computer method was not precise, and I showed you where it is good and where it is not good. So I'll show you some more examples. And if you want more examples, you'll have to refer to some of our papers or the theses of my students. But you will see some more examples. The fuzzy examples I gave you Not all of them were good, no. The benign one was good, but the malignant ones, some extra regions were included, some regions were lost, and after fusion it became better. But the initial results, no, they're not perfect, no. They work to some extent, and they do fail in certain parts. Speculations are hard to include. If there are 50 speculations, not all of them will be included. I'll show you some more examples of mass detection in another chapter 8. Is that what you meant? Yeah. Okay. Any other question or comment? We will switch to texture. As I mentioned, I'm skipping some parts. Some fine details I've skipped, sometimes a few pages, that you could easily read if you're interested in such detail. Unless you're going to implement, you don't need such detail. The general concepts I have explained. I've been going a little faster to create some space for the research seminars at the end. And if there is more time, I'll include a couple more topics that are not in that original list. With 10 hours for the first 3 modules and so on that I put, they're approximations. The course I give in Calgary has a total of 36 hours, but each hour is only 50 minutes, and that's over 13 weeks. So it's a little hard to estimate how that course goes and how this goes. So if I go a little too fast, please stop and ask questions, either during the lecture or after. And by going a little faster, I'll have time to talk about other research projects where you will see the practical application of some of these theoretical foundations. And here also I've been showing practical applications. Okay, we looked at shape analysis, and we also noted at the end that shape by itself is not everything. All the internal details have been thrown out. All the details of the surrounding regions have been ignored. So just shape can give you some information, but not all. So we noted at the end we need additional measures to get better representation of whatever it is, tumor or calcification or some part of the body. And texture is one such measure that takes into account variations in intensity, grayscale, density, whatever the parameter of the image represents. So there are several examples of texture: wood, cloth, brick, and so on. This is texture. This is repeated texture, the same thing happening, different color too. And there is texture there, those stripes, vertical. And on the wall, there isn't any texture here, but there's no brick here. If there is brick, you will see some type of a rough texture. Clouds have some texture. So wood has some grainy texture here. So there are various types of texture, and you may categorize them as periodic and random. Periodic could be quasi-periodic, not exactly periodic. This is periodic, but you don't find such periodicity in a biological being. So if there is repetition of a texture element at almost regular periodic intervals, then you call it periodic or ordered. Ordered texture is another name. And the elements of such a texture are called textons, like these are textons. What is a texton? Maybe this blue line and green line. It's hard to say, or you may say it is the little square. It's up to you as to what you are seeing. You can say these are arrangements of little squares, green and blue and white. So then the texton is a little square. In that case, a texton is that big stripe. Brick walls and floors with tiles are examples of periodic texture. The same thing is appearing here, the same tile. If no texton can be identified, texture element texel or texton, such as clouds and cement wall surfaces, there is some roughness, but you can't see any, there is some graininess, but there is no geometric pattern or motif. In some shirts, floral design, there are the same motif is repeated. Then that is the texton. But in the case of a cement wall surface with some roughness, that is random. There's a book by Rao on texture analysis, and we have used some of his methods. And there he includes the category of weakly ordered or oriented texture. And oriented texture is so common in medical images, and oriented patterns are common, that when I started writing this book, we had already done some work on oriented pattern analysis. I started putting them all together, and that became quite a big chapter. So you will see, oriented pattern analysis has many applications in biomedical image processing. And Rao took or showed these examples, or discussed these examples. Like hair, I don't have much left there, but hair is sort of oriented pattern, wood grain, brush strokes in paintings. He said these are all oriented patterns. It's not always like that, there could be different orientations. Texture could also be related to visual or tactile sensation. When you feel the surface, you may feel some texture, and that is tactile. Fine, coarse, smooth, granular, periodic, patchiness, mottled, or preferred orientation too. So some of these, if it is not just a picture, but a real object, you may be able to feel, so it is tactile also. So this is something based on what we see, but Haralick and others said texture is statistical, or you can describe texture using statistical measures related to the spatial distribution of gray level variation. The spatial variation actually is not included, it's just a histogram, but there is co-occurrence. So by taking pairs of pixels, or pixels with a certain separation, a little bit of spatial dependency is brought into account. So Haralick's papers have been very popular, and their Haralick and others, colleagues, and their papers have had huge numbers of citations. So about citations, I want to tell you, whenever I mention Haralick, I remember this. When Google started coming up with these H-index and citation record and all that, some 20 years ago, I didn't know that. One of my colleagues who was very much into this came and said, we should do all assessment of professors, departments, and so on must be done using this index, that index, and impact. And okay, I don't know that. I have never seen that. And then he said, your impact or whatever that number is very good. I said, okay, good. I hadn't seen that. And then we started looking at this on a routine basis. Go to Google Scholar, I got 2 more click and be happy. So I have, it's getting close to 20,000, let's say. At that time, maybe I had 10,000. My friend said, this is good. I said, okay, I'm happy. And then I saw some other papers. And this paper by Haralick has more than all of my papers in my whole life combined. One paper. And the papers by Hu on moments, and the thresholding technique by Otsu. They're short communication papers, but they have more. So then I said, wow. So I tell such stories to my students. What are the term? What's the term? Ego boosters and ego busters. So I look at my number, I say, 15,000. So my ego is boosted. Then I look at Haralick and one paper, and the balloon is pricked. So one should look at the global picture. So in biomedical images, texture does appear, different types of texture. Oriented texture is common in medical images due to the fibrous nature of muscles and ligaments. Muscles have muscle fibers. We can't see them. X-ray images won't show the muscle fibers. They are very thin. But the ligaments and ducts in mammograms show up in the breast, show up in mammograms. And blood vessels, veins, ducts, nerves, they are sort of curvilinear structures. They're linear in a small portion, but in a full organ, they will be curvilinear. A preferred or dominant orientation is associated with the functional integrity and strength of such structures, as I said about ligaments. I'll show that later on when we go to chapter 8, which is completely on oriented texture. Ordered texture is found not so much in the human body, but skins of reptiles, snake skin, the same pattern appears. But there is some size variation, orientation variation. It's not exactly periodic. In the retina, there are some patterns that are repetitive. In the cornea, the compound eyes of insects and honeycombs. A honeycomb perhaps is the best example. But I tried to get pictures, and I only got honeycombs that were artificially manufactured. They do that and put that in the whatever that box is for the bees, and the bees go there and do their stuff. But later on I did find some, but they were not showing what I wanted to see. Liver and other such organs are made up of clusters of parenchyma, tissue that are of the order of 1 to 2 millimeters in size. The pixels in CT images used to have 1 by 1 millimeter. Nowadays they are better. But suppose your imaging system has resolution of the order of the size of the parenchymal clusters. Then, with ultrasound imaging, the wavelength of the probing radiation is of that order. But again, technology has changed. Ultrasound also is now into the 4-5 megahertz range. So under these conditions, when the wavelength of the probing radiation or the resolution of your imaging system is of the same order of magnitude, not the same, but order of magnitude of the clusters present, tissue clusters, then there is speckled and random texture. So random texture is more common. So this is part of the liver of a patient, the speckled and mottled appearance. I zoomed in. The size of each image is 55 millimeters square. That's the true size. That's the kidney in a CT image. These are CT images. This is the spine in a CT image. There is some randomness in variation. I wouldn't call it random texture, not as much as that, but there is some variation. This is not texture. These boundaries are not texture. But what is inside here could be taken to be some sort of texture. And this is oriented texture, branching, patterns in the lungs. So that is a different type of texture by itself. Oriented, well, yes, there are some oriented patterns, but they keep branching, so you have all orientations eventually. Parts of mammograms, each part is, these three are 60 millimeters square, this is 40 millimeters square. So this is oriented, but there is a preferred orientation there is a preferred orientation here, but this is random, cloudy. You don't see the ligament structure, the fibroglandular structure here. But this is also a part of a mammogram. So within the mammogram, you could have random texture, oriented texture here. That orientation is not clearly seen there. Here it is sort of mixed up. There are oriented parts here and there. So that is what is oriented texture. Periodic, this is endothelial cells in the cornea. This is part of a fly's eye. Each one of them is an eye of the fly. And this is the belly of a cobra. This is periodic. That is sort of periodic by itself, but different pattern. But this, because of the curvature, the projected image shows these with distortion due to projection. Otherwise, I suppose they are of the same size and shape. So this is periodic texture in biological, not biomedical, but this could be medical if they use it for some diagnostic application. There are some interesting models for the generation of texture. How do you generate texture? Interestingly, I wanted to study this, and because I have also studied speech signal processing when I was a grad student at IISc Bangalore, I took a course on speech signal processing. I remembered some of that, and these models and speech generation models have very similar patterns. There are similarities between speech and texture generation according to this spot noise model. The types of sounds produced by the human vocal system are voiced, unvoiced, and plosive. Voice sounds like ah, ee, oo, they are periodic or quasi-periodic. There's a wave like that and it repeats. The waveform changes with the type of the vowel, but if I just change the pitch, I say ah, ah, or higher pitch, the waveform remains the same, but the interval, the pitch will change. Unvoiced is one of them is a fricative, like S and F and J. Or I shouldn't say S. S has A at the beginning, which is a vowel. So I should simply say S, like a snake. That is a fricative, or J. So that is random, but it is filtered random noise. And plosive, where we stop, close the mouth, and go P or T or K also to some extent. So there's those who call plosive or stop signals, where the signal is stopped and then suddenly there is a burst. The first two types get the plosives out because it's a discontinuity in the signal. It's a transient, so you deal with that separately. The first two types, voiced, unvoiced, are the two important types, and they are modeled as the convolution of an input excitation signal with a filter. And the model is that we have the vocal system here, and we are sending puffs of air. We are pushing air from the lungs through here, and we have the vocal cords. If the vocal cords are engaged and they vibrate and open and close, we are producing the voice sound like ah. There is repetition, you can feel here ah, and you can feel the vibration. So the air coming from here is modulated, and we get that signal. When we say s or f, then there is no engagement of the vocal cords, they don't vibrate, the glottis. We are simply pushing air through a constriction like s. The constriction is here. Or f, it's near the lips. So when pushing air through a constriction, you are modifying the spectrum of the input, which is random. So you are filtering, but it is still a random signal. There is no definitive waveform to that. The excitation signal is quasi-periodic when we use the vocal cords to create voice sounds, or random in the case of unvoiced sounds. So this is the standard speech signal generation process: random excitation or quasi-periodic excitation. If you use random, you get unvoiced. If you use quasi-periodic, you get voiced. The vocal tract from here to the lips and to the nose, nostrils, that acts as a filter. And how you shape it determines the speech you are producing. A funny thing you can say here is all the speech, my entire course and all the lectures, all the songs, all the music you produce, it's just hot air. You're pumping air through. But hot air means rubbish. So it is air being modulated. The modulation is important. The same can be done here. In the Texton model proposed by Ulish and others, we have random field of impulses, random excitation, random field of impulses, 2D, and quasi-periodic excitation, a period of a periodic train of impulses or pulses. Here, ordered field of impulses. And select between the two, and there is a filter, which is a texture element or texton or spot filter, a point spread function. Same model. And you get a textured image either with random or ordered patterns. And the texton could be isotropic, it could be a flower, it could be a line, it could be an oriented pattern, it could be anything. Texture may also be modeled as the convolution of an input impulse field with a spot or texton that acts as a filter, like speech. There is no physical vocal tract there, it is just a picture. So this is, not Eulish, Van Wyk, the spot noise model for synthesizing random textures. So the Fourier spectrum of the spot acts as a filter that modifies or modulates the spectrum of the 2D random field. Convolution becomes multiplication in the frequency domain. Ordered texture may be generated by specifying the basic pattern or texton to be used and a placement rule. The placement rule need not be periodic. You say, I want this pattern repeated. Like a flower, put here, there, and keep stamping. That's how they make saris and printing, block printing, or clothes with the same block is printed on cloth. Typically periodically, but there could be other patterns where it is not periodic or quasi-periodic, and you just have to say, put it here, 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 and that means you're putting an impulse at those locations, convolving with the spot. Convolution will copy the spot at every impulse. So then that spot becomes a filter. It acts like a filter. Okay, let's stop here. I'll have some more examples coming up. Coffee here, or shall we just break anyway?
3 o'clock.
I'm sorry?
3.
Oh, 3. Sorry. I was thinking about yesterday, I suppose. Yesterday I had a small lunch perhaps. Okay, we'll continue. So essentially, the spectrum of the noisy random texture image will be the spectrum of the spot filter, because it is the other input spectrum of random noise is flat. So here is a noise field, computer generated, and its spectrum. I took the Fourier transform. It's almost constant. This is not constant. There are some variations here. When you map for display, you will see some variations, but that is supposed to be constant. So here are 2 spots, circles, 2 circles, approximate circles. Their Fourier transforms we saw earlier. The Fourier transform for circle is a Bessel function with this ring-like structure and with aliasing artifacts there, or some high frequency artifacts, because these are not perfect circles, they are on a discrete grid. And if you convolve this with that noise field, each time you generate a noise field, it's different. In some cases, I generated a noise field and kept the same and convolved. So if I convolve with this with the noise field, I get this. If you convolve with that, you get this. So these patches are a little bigger than here. So this is filtered noise. And look at the spectrum of this. The spectra of these 2 images are the spectra of the spot multiplied by the spectrum of the noise, which is flat. It's essentially constant. So the spectra of the texture patterns are essentially the same as the spectra of the spot. Okay? It's a square patch, and that's the texture you get, the spectrum of the square, and this is 2D sync function, the spectrum of that. This was convolved with the same noise pattern, and the spectrum of this is essentially the same. some hash pattern, and the texture and this and that are essentially the same. Okay. Ordered texture, as I said, you're just placing the same pattern, and you can say there is a certain pitch or repetition rate or distance of separation between the copies of the texton you place in the x and y directions. And that is also convolution of the impulse field with the texton. So the difference between the ordered and the random texture lies in the structure of the impulse field. One uses quasi-periodic field of impulses. The other uses random noise. Random noise is also a bunch of impulses. Every pixel is like an impulse. If you were to break a signal into an impulse train, we saw earlier, you can represent any signal as a bunch of weighted impulses. The same in 2D. So one is a periodic train of impulses or periodic field of impulses. The other is random noise. The spectral characteristics of the texton act like a filter that modifies this. Orthogonal to that, you will see concentration of energy because of the sinc function corresponding to that line. If it is a thick rectangle, then it will be a 2D sinc function, but one axis will have more depending upon the orientation and thickness of that line pattern. So you can provide line segments or oriented motifs, not a flower that is isotropic, but a line. And then you get oriented patterns like this. I hope you can see that. There's a line there. That's the texton. When I convolve that with the noise field, I get that. That's oriented texture. Lines of various intensities. The Fourier transform of the texton and the image. But for some scaling factor and noise in computation, they are the same. Okay? Analysis of texture could be done using statistics or structure. The two main branches of analysis of texture are statistical and structural. Structure implies the use of measures to represent the texton and how they are placed. You need to identify some pattern in order to describe structure. But you can also say it is composed of line patterns like this and so on. But there is no specific placement rule for this ordered texture I showed just now, this oriented texture rather. If you have some other texture, you can say this is placed above that and left and right, there are these things, and that becomes structural analysis. Parallax measures are based on statistical analysis. But before we go to that, let's look at some basic measures of texture in terms of statistical measures. We could start with the simple moments we have already seen. The kth central moment mk is L minus mu f to the power of k PL. PL is the PDF, but only one gray level at a time. So zeroth order histogram, as we talked about earlier, turned into a PDF. L is the gray level, mu is the mean to the power of k. If k is 2, then that is the variance. There should be a 1 over, no, this is PDF, so there is no 1 over n. Mu is LPL, the moment with only L here. So the variance is a second order square here, L minus mu. So this is important as a measure of inhomogeneity, in the sense there is gray level variation. That's all you can say. skewness, the third moment normalized by m2 to the power of 3 over 2, or the square root of the third, the standard deviation raised to the power of 3, or kurtosis, the fourth moment with standard deviation raised to the power of 4. M2 is variance. Standard deviation is square root of that. So skewness and kurtosis indicate that the PDF is not symmetric. It is skewed towards one side. They are basic statistics, but we need to recognize what is important in the given application, what is the distinction between the categories, benign, malignant, or so on. In vertebral compression fractures, we found kurtosis to be useful. I'll show you that later on. But high order moments are affected by noise or error in the PDF or in your measurements, and they may not be reliable. But going up to kurtosis is commonly done. There should not be any difficulty up to the fourth moment, but if you go further, then noise becomes an issue. In mammography, Bing and others computed the skewness of histograms of parts of mammograms. An average skewness measure was computed for each image by averaging the section-based skewness measures for a mammogram. Mammograms of breasts with increased fibroglandular density, known as dense breasts, were observed to have histograms skewed towards higher density. There were more pixels with higher density values. That indicates higher breast density. And if that persists with age, if the breasts are dense at an increased age, that would indicate susceptibility of the development of cancer. Not that it will happen, but increased susceptibility. So mammograms of fatty breasts tended to have positive skewness, whereas higher density gave negative skewness. So that was shown to be a good feature, just one feature. So the skewness measure was found to be useful in predicting the risk of development of breast cancer related to higher breast density or tissue density in the breast. So that's a basic application of one of these four very basic statistical measures. Now, Haralick's measures are not based on that PDF of 0th order, but instead taking pairs of pixels into account. So you look for co-occurred so many times, two occurred so many times. Whereas here, you look at pairs of pixels. Given a pixel, you ask, what is the value above? What is the value to the immediate neighbors? One pixel above, left, right, and bottom. Or you may say, I will use a spacing of 2 pixels. So the current pixel and 2 pixels away, what is that value? And then there are multiple possibilities. A distance of 2 pixels, take all the pixels in the neighborhood and take their joint. Okay, 6, 6, and 6, 5, and 6, 4, and 6, 7, and you have pairs of those pixel values. So they are based on the moments of a joint PDF that is estimated as the joint occurrence or co-occurrence of gray levels, known as the gray level co-occurrence matrix. If you have 255 levels, you have 0, 1, 0, 2, 0, 3, 0, 255, 1, 0, and so on. There are 255 square possibilities of pairs. Now you could also take 3 at a time, 4 at a time, and so on. Then you get to higher and higher order moments. Statistical combinations. We saw that earlier in talking about measures of information. It's not just PL, but P, L1, L2, L3. 3 levels together, or L1, L2, L3, L4, 4 levels together. But how are they placed? How is that string placed in space? You need to define a pattern. Here, you need to define in terms of displacement. What is the distance between this pixel and the other pixel you're considering to make a pair? And what is the angle? Above, below, left, right, or some diagonal, whatever angle. So 2 parameters, distance and angle. If you don't care for the angle, you can say any adjacent pixel, left, right, top, bottom, doesn't matter, they're all equally adjacent. You count them all. Put them all into one matrix. Sometimes that is done. Sometimes you take angle into account in forming the GCM, gray level co-occurrence matrix. It is also called spatial gray level dependence matrix, SGLD matrix. So you compute for various orientations and distances. So the GCM could be defined as P, capital P, the count of occurrences of L1, L2 separated by d theta. D is distance, theta is angle, like in the radial coordinates or polar coordinates. The probability of occurrence of the pair of gray levels L1, L2 separated by a certain distance d and angle theta. So GCMs are constructed by mapping the gray level co-occurrence counts or probabilities based on the specified spatial relationships at angles theta and scanning the image with the distance d, left to right, top to bottom. Now neighboring elements in natural images tend to have high correlation or nearly the same values. So GCMs tend to have large values along the diagonal of the main diagonal of the matrix and around them. If a pixel has the value 55, quite likely the neighboring pixels are 55, 54, 57. You don't get 200 or 0 there. Those values could occur somewhere else in the image, unless you're at an edge. And low values away from the diagonal. So these matrices have some general properties. So for an image with b bits per pixel, we have L going 2 to the power of b gray levels. The GCM is of size L by L. So if you have 256 gray levels, this will be 256 square. If you have 10-bit quantization, 1024, then 1024 square. And with CT images, if you have 12-bit, then it is that square, 2048 square. No, 2048 is 11, that is 4096 square. So fine quantization it's right here, I'm jumping ahead. With 2 to the 12, 4096 in medical images could lead to really large gray level co-occurrence matrices. But with such fine quantization, you may not find pairs of values. There'll be large differences, and you may want to re-quantize such images to a smaller number of gray levels and compute the GCM with a smaller matrix size, re-quantized to maybe 8 bits or even 6 bits. Then you may get better properties free of noise. In a noisy image with fine quantization, the GCM may not give you a good number of counts in many of the bins. So in practical applications, we need to consider this. If you have a 1000 by 1000 image with 12-bit quantization, you have 1 million pixels, but you have 4096 square bins in the gray level co-occurrence matrix. That's a mismatch there. So you want to reduce the number of gray levels to a relatively small number before computing the GCMs by re-quantizing, averaging and re-quantizing, maybe some filtering. GCMs are commonly formed for unit pixel distances and the 4 directions, 0, 45, 90, 135. That is top, bottom, left, right. And if you want 8 connectivity, you can consider the 8 connected corners in the 3 by 3 neighborhood. But the distances are not equal. We should bear in mind if any distance related measure is to be taken, then left, right, top, bottom distance is 1, but the diagonally connected elements, the corners, have a distance of √2. Mostly that doesn't matter, but in some cases that may be required. Well, this is my right eye. You have seen my picture earlier. I took that piece, and it's a 16 by 16 pixel image, and I re-quantized to 3 bits per pixel. So the values are between 0 and 7, and those are the values. And now you take, this is 1, so you have 1, 1, 1, 0, and come here, 1, 1, 1, 1, 1, 1, and so on. Or take this, you have 3, 1, 3, 4, 3, 1, 3, 1, you have 0, 1, 0, 1, 0, 1, 0, 2. So like that you scan the image and make this co-occurrence matrix. The current pixel, and here I used the next pixel below. I didn't add all of them. I said only looking below, so it's in a way causal, so I cannot do it for the last row. So here I said this is 1, 0. I didn't take that. This is 1, 1, 1, 1, and so on. So the direction is looking downward in the array. So the next pixel below, 0 through 7, these are the counts. Along the main diagonal you have, not so, there are some large entries here. This is the I, and there are rapid changes, black and white parts. So we don't have that main diagonal having large values, but there are some large values here. But if you go to the ends, these probabilities are lower. So yeah, in the middle somewhere here, you have large values. 0 and 7, 0 and 6 have not occurred. And similarly, 6, 0, 7, 0, 5, 0, they have not occurred. Okay? So that's the co-occurrence matrix, looking 1 pixel below the current pixel. If you do that for looking pixel to the right or top, and you'll get something different. Or if you say, I'll add all of them, I'll consider all of them, then you will get something different, average of all directions. If you don't want to be sensitive to direction, you may say, I'll take all 4 connected neighbors and count all of them. Okay, Haralick then said, Haralick and colleagues, they're known as Haralick's texture, but they are co-authors. This was PL1, L2 is the GCM. You normalize by the total number of values. So you call that treat it like a PDF, bivariate PDF, PL1, L2, small p. Now you take the marginals, integrate or sum this in one direction, L2, and sum in the other direction, L1, you get Px and Py. These are called marginals. And then Px plus Yk. Add the two, and PL1, L2, L1 going 0 to L minus 1, L2, all of the whole range, but L1 plus L2 must be equal to K. Then that is called X plus Y, K. There's only one index now. And similarly, X minus L1 minus L2 must be equal to K in magnitude. The sum of all these probabilities for all L1, L2 with that condition. So these were computed from the given GCM, and then a few measures were defined. Some of the basic measures one can understand easily and interpret. Some of the other measures, they are hard to interpret, and I have gone through their papers and I have not described what exactly the other measures represent in terms of visual features or any concept that we can understand and relate to. They are just statistical measures. But P square, it's like a second moment, P square L, like energy. So this is called the energy feature. That's easy to understand. A homogeneous image has a large number of entries along the diagonal, and large values go there, and the other values are small. An inhomogeneous image will have small values spread over a large number of GCM entries. So that leads to low F1, the other one gives you large F1. Large F1 means homogeneous, low means inhomogeneous texture. Contrast, you apply a weight K square, where K is L1 minus L2, multiplied with the probability, with the P L1 L2, which is a normalized GCM. Putting the weight K square, which is based on the difference of the gray levels. If the difference is more, and for large differences, the probability of occurrence of such pairs is large, this will be large. The correlation measure, L1, L2, P, L1, L2 minus the mean, mu x, mu y. Mu x, mu y, and sigma x, sigma y are the standard deviation values of the marginals, Px, Py. So this is the normalization factor. This is weighting by L1, L2 for P, L1, L2, and subtract the means. So this is interpreted as correlation. The sum of squares, it's like a variance, L1 minus mu f, PL1, L2, and inverse of that, 1 over 1 plus L1 minus L2. To avoid 0, dividing by 0, you add a 1 here. PL1, L2 will remain. So these are all moments of the PDF. This is a PDF. And you can take moments, you integrate the PDF with some weight. So what is the weight? That is the argument for the expectation operator or the moment that you are taking. It's like expectation. All these statistical moments, but these are the controlling factors. That is the PDF. Here, you are taking the difference in the denominator, so it is a measure of homogeneity. If the differences are large, it means heterogeneity, but it's in the denominator. So it is homogeneity. Some average, they took the px plus yk, moment of that. Some variance, the variance of that, px plus y. The probability of the sum of those values. Some entropy. So there are a few measures of entropy. Entropy is p log p, as we have seen. But which probability? X plus y, log of that. And another measure, this GCM, normalized GCM, PL1, L2, log of that. So these are just entropy measures. Here the sum PDF is taken. Here the original PDF is taken. And then the difference, X minus Y. Another entropy, difference entropy. These measures are a bit hard to interpret. The 12, 13, 14, I didn't find any explanation or physical interpretation of these in the original paper or anywhere else. So the previous measure, no, they're not here. They'll come later. There are entropies hx1, xy, and xy1, and the max of hx, hy. That is 12, and 13 is this, where these entropies are, xy1 is the entropy of PL1, L2, but log of the px and py. And here you have the product px, py, and log of that. So they define two more measures of entropy and combine them here. Why or what does that represent? I could not find a suitable interpretation. And the last one is further complicated. Complicated in the sense something is being done, but there's no interpretation given. The probability PL1K, PL2K divided by PXL1, PYK. I found this expression a bit awkward. There is something wrong, but I checked with my colleague and checked with other sources. I even wrote to Haralick. This, I don't know if that should be K. Yeah, that should be outside. It is independent of this summation. It should not be inside. Maybe they wanted it to be K.
With reference to L1.
But why is it inside? It should be outside. The summation is on K, and take that out, independent of K. It's with reference to L1, yes, but there is no meaning given to any of this. So in practical applications, there are many papers that have said, well, we tried all the 14 and the first 3 or 4 or 5 were adequate. So there are many papers where they have used only the first 4 or 5 of these measures, which can be easily interpreted. The others have not found much application, because they're hard to interpret, or maybe they haven't worked well. We have also used all of them. We have included them in our projects because we need to compare the performance, and they may contribute in some sense to our pattern classification problem. So these are popular measures, all the shape factors we saw, whose moments, and so on, and Haralick's measures. If you don't use them, the reviewers may question, did you try these and did you compare? So, at least for that purpose, but these are known, well-known and well-established, so you could try them, and if they work, that's good. If the dependence of texture upon angle is not of interest, GCMs over all angles may be averaged into a single one. As I said, instead of just looking at the pixel below the current one, you can say, well, I'll count the one above, left, right, and below, and take all of those 4 counts and throw them all into the same GCM. Then you're not sensitive to orientation. Distance D, it should be taken into account according to the sampling interval and pixel size and the size of the texture units of interest, or you downsample the image. Resample or downsample the image and recompute. And at some resolution you may get good results and not at other resolutions. We found that in mammograms, a resolution of 200 micrometers is good. Not 100, not 50, not more than that. 400, no. So there is a certain limit in the resolution at which these measures work well. Texture. If you use too fine resolution, then you may not get meaningful counts of a co-occurrence. And if you use too coarse resolution like 400 or 800 micrometers, then you will lose information. So the angle and distance d and theta need to be accounted for depending on the application, the resolution of your image, and the expected spatial size or dimensions of the patterns of interest. So normalization to a range such as 0 to 1 over the data set may be beneficial. Or you may normalize by dividing by the standard deviation of each feature. So we'll stop here and continue after our coffee break. 30 minutes?
Yes.
3:30. Thank you.
Break for tea now. Keep that in mind.
The image, then the GCM should have large values along the diagonal corresponding to the gray levels in the texture elements. So the chi-square statistic was computed, this PL1, L2, and this marginal and normalized by the marginals. And the measure was normalized by dividing by L. It is expected to possess a high value for periodic texture under these conditions. And then they proposed a measure of agreement, kappa, as P0 or P0 minus PC or 1 minus PC, P0 being the sum of PLL over all L, and PC being the marginal probabilities combined this way. And they found that, or showed that, this kappa has maximal value of unity when the GCM is a diagonal matrix, which indicates perfect agreement of or periodic texture. So they showed that texture analysis can be performed with appropriate D and theta to detect periodic texture. Chan and others who have worked on, who have published many papers on mammography, they found correlation, difference, entropy, and entropy to perform better than the other features. They tried many of these features. And we have seen many other papers where not all the 14 texture parameters have been found to be useful in practical applications. So 3 to 5 of them have been found to be useful in practical applications, and many studies use only the first 5 or so. Sahina and others developed what they call a rubber band straightening transform to map ribbons around breast masses. Okay, this is beginning now. into rectangular arrays and then computed Harlick's measures of texture. The point or the problem or the issue is these co-occurrences are defined on a rectangular grid or on a rectangular image. You need to look for neighbors and scan in a certain way. But if you have some irregular shaped objects like a calcifications are too small, let's say tumors, then it'll be, many of the pixels may not have neighbors for the d theta parameter specified. And then the counts for such parameter values in the GCM may not be meaningful. So it's been shown to be advantageous to convert the region for which you are computing texture when it is not a rectangle into a rectangle by mapping in some way, geometric transformation. And also in the case of breast masses and tumors, what is inside the core of the tumor quite often is not important. The texture inside may not be important, but what is around the ribbon or the periphery of the tumor is more important. That is, how the mass is interacting with the surrounding tissue. In the case of a benign mass, there is not much interaction. There is a sharp edge and the mass is sort of contained. In the case of a malignant tumor, it is spreading, so there is some interaction and the surrounding tissues are being disturbed and modified by the malignant or cancerous tumor. So then it is that periphery that is important around the tumor and not what is at the core of the tumor. So Sahainer said we will take that, but it is a thin ribbon of some odd shape and size. The thickness is fixed, but the shape could be something different for each image. But how do you compute the texture parameters? They said, okay, we will stretch it into a rectangular ribbon. So they called it rubber band, like a rubber band, and make it rectangular. My PhD student, Naga Mudigunda, he took a different approach. He used adaptive ribbons of pixels extracted around mammographic masses and tumors and used the features to distinguish malignant tumors from benign masses. So we will see some of that later on in the application part. There's a paper by Loss who came up with a different notion for texture known as texture energy. It is not based on counting pixels, but instead computing a measure of energy after applying certain filters to the given image. So he said the texture energy could be computed by taking the energy of a filtered version of the given image. The filters determine what kind of energy you are computing or what kind of pattern is being represented by that texture energy. The texture energy features represent the amounts of variation in a sliding window, so you are computing energy in a small window and making another image and then using that as a feature. The filters are specified as separable 1D arrays for convolution, and then combining the 1D arrays you get 2D operators. So the 1D operators were defined in this manner, 1 to 1. Now when you take one of these and multiply with the transpose of the same or another, then you get 3 by 3 matrices. So 1 by 3 times 3, or 3 by 1 times 1 by 3 will get 3 by 3. So 3 by 3 mass were generated by multiplying the transposes of each of these three operators with their direct versions. So L3T, L3 transpose E3 gives one of the 3 by 3 Sobel masks, like a differentiation operator. And then operators of 5 pixel length were generated by convolving L3, E3, S3 in various combinations. When you convolve a string with 3 values with another string with 3 values, you get 3 plus 3 minus 1, 5. And then those were combined in this manner, taking the transpose of one and another, and L5, T, E5, and so on. I don't have all of those numbers here. It's not important, but the basic operators are these, and they were extended to have the length of 5, and then they were combined, the transpose of one with another, to make 5 by 5 operators. And there are gradients and edge and spot detectors of various kinds. So when you convolve the image with these, you are detecting such patterns. And the image will have positive and negative values for these operators. You square, and then you take the energy of that. So these are the operators of length 5. So this is convolution of one with another. So these were called local average, edges, spots, ripples, and waves. Detection of those patterns. So depending on what kind of patterns you have in the image, one of these, or the corresponding one of these, will give you a high energy in the output. And then they made 5x5 operators further, taking L5 transpose L5 or L5 transpose E5 and so on. So this is the familiar Lena image, but she is not popular anymore. Journals are now telling not to use this, so I have removed her from the book. This was, I think I mentioned that, in the 70s and 80s, not many labs had image digitization equipment. And there was an image processing lab at one of the universities in the US. They made these available on some sort of a website, or there were no websites then. Some downloading FTP facility. So researchers got those and wrote papers. We also did the same. But now journals are telling, an interview was done with her, and she said she was happy that so many researchers were using her pictures. Nobody shows the rest of the picture. So this is the original picture. This is after the smoothing operator, ELF. No, this is with L5, L5, and then it is going this way, sorry. B is L5, L5. No, A is L5, L5, B is E5, E5, C is W5, W5, and these are by taking the sum of the absolute values of these results in a 9x9 moving window. So you have to average this. Here you have positive and negative values. You can take the sum or square, and these represent the energy, texture energy as called by Laws. And these were mapped for display. So it's not exactly the values. For example, the full range was minus 1338 to 1184, mapped to 0 to 255. So mapping will sometimes shrink the effect of the display. Fractals can also represent texture. There are many methods of generation of fractals. The most common definition is a pattern composed of repeated occurrences of a basic unit at multiple scales and in a certain order of generation or placement. This is known as self-similarity. The same pattern or motif appears, but at multiple scales and in a certain ordered pattern. It is also seen as a nested recurrence of the same motif at smaller and smaller scales. Nesting is when one goes inside another, but sometimes it might not be going inside, but they are placed in some order. In nature, we find many fractals, and Mandelbrot said mountains are not triangles and clouds are not spheres. They are modulated by repeated occurrence of multiple scales. So a mountain, if you draw like this, that's one basic mountain. But then if you put more and more triangles and keep subdividing those triangles into smaller and smaller triangles, then you get a real mountain. The same with clouds. You take a circle and make it macro-lobulated, take each lobule and lobulate it again in 3D, then you get a cloud. So that kind of a pattern is also a fractal. The motif is like a triangle or a sphere, or some kind of a pyramid and a sphere in 3D. The self-replicating patterns of the leaf structures of ferns, I'll show you a picture. The ramifications of the bronchial tree in the lung, I showed a CT image of a part of a lung with those branching patterns. That is also a fractal. You start with one tube and it branches, and take each branch and keep doing the same thing. They become smaller and smaller, but that is a fractal. And that happens in the arteries of the heart also. So that's a fern leaf from our garden. So the same pattern occurs. The whole thing looks like that. And then you look at one of these, it looks, if you were to take this and expand, it will look like the whole thing. And take that and expand, it will look like that, but there is a limit. There are only 3 scales. Beyond that, if you take this, there is nothing more. So it's a physical object. So the number of levels of this is limited. Whereas in computer-generated fractals, you can keep zooming and you can keep generating more and more. But that is simply replicating the pattern and recreating it. It's not there in the original image. If you zoom, just take a static image and zoom, you'll start seeing pixels. But what is displayed in computer animated displays of fractals, the same pattern keeps appearing, looks like infinity. But had it been a static one print and you zoom in to a factor of 4 or 5, that pattern doesn't exist anymore. So if your image is of a fixed number of pixels, yes, the same pattern occurs at smaller and smaller size or scale, but if you zoom in at some point, that pattern is lost. And the same in true physical entities also. You need some material to make this. And the material takes up some space and some material, space. So you cannot have this pattern to infinite levels of resolution. But that is a fractal. So fractal, in some cases you can come up with a dimension and say there is a certain number of stages of this happening. In some cases you cannot put a specific number. The fractal nature is related to complexity, and that is expressed in terms of a fractal dimension. If you were to take a straight line, it is a 1D function, but if you take a function of time that is varying, or some one-dimensional function with variation, that is not one-dimensional, it is between 1 and 2 dimensions. In order to plot it, I need a 2D surface, the board, to plot that. But it's a 1D function of one variable, but it's not a straight line. So the Euclidean dimension of a straight line is 1, but that of a curve or some signal like a speech signal or ECG is not 1, it's not 2, it's 1 point something. Similarly, an image, it's not flat and smooth like this, so it's not just a flat 2-dimensional surface like the board, but it has some gray level variations which could be seen as variations in height. Then it is sort of between 2 and 3D. So the fractal dimension will be more than 2 but less than 3, and so on. So this is the notion of fractal dimension. So one of the common examples given is that of measuring the length of a coastal line. They always go coastal line of England. I don't know why it cannot be Mangalore or some other place. Any coastal line will have these irregularities. So if you go and walk on the beach, how do you measure the distance between 2 points? So if you just put a straight line, straight ribbon or a ruler and measure, then you get 1, but you are missing all those other details. If you start measuring all the details, it depends on the size of your ruler as to how big your ruler is. I don't have a ruler here. There is something. You measure this 1, 2, 3, 4, and so on. Any detail that is smaller than this will be missed, skipped. So you take an even smaller ruler, 1 millimeter, and start measuring 1 millimeter at a time. Then the distance or the length of that coastal segment will be longer and longer and longer, with finer units of measurement or the scale of measurement. So if it is a straight line, then no matter what the size of the ruler is, you will get the same value always for a straight line. So that's another notion of a fractal, where the measure that you get depends on the scale of your measurement. So use of a larger ruler to measure the length of a coastline, minor details in the border having small scale variations will be lost. And a certain length is derived. If a smaller ruler were to be used, you get a larger length between the same two endpoints. So this relationship is expressed as L eta. Eta is the measuring unit, the size of your ruler. L eta is the length measured. DF is the fractal dimension. And L naught is some constant, the size of that ruler that you're measuring in millimeters or centimeters. So the fractal dimension comes up in this relationship. You take the log and you get this relationship. The log of the measured length is some constant plus the log of the scale with 1 minus df as the slope of that relationship, and df is the fractal dimension. For a straight line, df is equal to 1. So you get one quantity. So this is known as the ruler method or the caliper method to estimate the fractal dimension of a curve. You could view fractal dimension as a property of that curve as to how it fills space. There is a certain space and you could fill it. If you just have a straight line, it only takes up that much space over your grid. But if I draw some other pattern, it is taking more space. But it is still a line. The fractal dimension of a straight line is unity. That of a circle or a 2D perfectly planar sheet light object is 2. That of a sphere is 3. But as the irregularity or complexity of the pattern increases, the fractal dimension increases up to its own Euclidean dimension plus 1. So there are space filling curves. It's a one-dimensional curve, but it will fill a 2D space, like the piano Hilbert curves. The fractal dimension of a jagged, rugged, convolution here is not mathematical convolution, but something that is wrapping on itself. Kinky or crinkly curve will be greater than unity and reaches the value of 2 or approximates or move towards the value of 2 as its complexity increases. And in terms of images, the fractal dimension of a rough 2D surface or image will be greater than 2 and goes towards 3. So in that sense, it's a measure of roughness. So you need to recognize what you are representing by this parameter. There are a few more definitions. There is one called relative dispersion. RD of eta is the ratio of the standard deviation to the mean using varying bin size. So RD eta is the reference. RD eta naught is a reference value for the bin size, and eta over eta naught to the power of h minus 1, where this h is known as the Hurst coefficient. And the fractal dimension df is given by the Euclidean dimension de plus 1 minus h. So de is 1 for 1D signals, 2 for 2D images, and so on. So the value of h and from that the fractal dimension may be estimated by measuring the slope of the straight line approximating to the relationship of log of what you're measuring to log of that, the scale of measurement. And the same applies to the ruler method and a few other methods. There is another model known as the fractional Brownian motion. So here, the expectation value of the difference, f eta plus delta eta, some displacement minus f eta. It could be a function of time, space, whatever. So the displacement is delta n, delta eta here. And expectation of the absolute value of that is proportional to delta eta, that displacement to the power of h, the Hurst coefficient. So again, you take the plot of the average difference as above versus delta eta on a log-log scale and fit a straight line and use that slope to estimate the fractal dimension or the Hurst coefficient, and the two are interrelated. So there have been many applications in medical imaging and image processing. Chen applied fractal analysis for the enhancement and classification of ultrasonographic images of the liver, and there are many. Benign masses have been modeled as smooth homogeneous texture, malignant as rough and heterogeneous, and they have higher fractal dimensions. But the difference is not that much. They have to be between 2 and 3. So the difference is like 2.4 to 2.5. Is that enough for pattern classification? It depends upon their variance also. The path spectral density of a fractional Brownian motion signal, phi of omega, taking it for example to be a 1D signal of time, for example, is 1 over omega to the power of 2h plus 1. The derivative of a signal generated by fractional Brownian motion is known as a fractional Gaussian noise signal, and the exponent in the power law relationship is this, for that is 2h minus 1. But here in the path spectral density it is 2h plus 1. So this is known as the power law. So how do you analyze texture using this? Based upon fractional Brownian motion model, this intensity difference IdK was defined, where you are taking Fmn is the image, Fmn plus k some displacement, and sum on that, sum on m and sum n going n minus k plus 1, and plus in the other dimension m plus kn for k as an argument of k. So you compute this for different k, and a slope of this log idk versus log k was used, and to that you fit a straight line, get the slope, get h, and from that the fractal dimension. And they gave various accuracies in the classification of ultrasonographic images of the liver. There is another. Bing came up with this method of surface area measure, where it's also known as the blanket method. Suppose you have this plane surface of the table and you want to cover it, you need a sheet of that area. But suppose you have all these objects and you want to cover all of them, you need a larger sheet to wrap around all of these. So if this area has lots of ups and downs and pillars and objects of various heights, then you need more and more of this blanket or sheet to cover all parts, including all these exposed parts. So that is known as the blanket method for that reason. So a flat picture with no variation requires a minimum area of the blanket to cover, and then more variations in texture or height of the pixels means larger blanket. So that is what is characterized here. Let me go to that. There's a picture there. So these are like buildings in downtown or somewhere. Let's say they are adjacent, and you want to cover not only the top areas but also these exposed areas in between the blocks. If all of the blocks have the same height, then you don't have these exposed areas in between them, right? So the total surface area of the image is eta square plus eta, the difference between the adjacent pixel values. So if the differences are 0, then you just have eta square and as many blocks as you have. So again, you do the same thing. Take log of eta versus log eta and plot. And it is some curve at a straight line to approximate the slope. And in this case, you need to have some adjustments for the Euclidean dimension of the source. If it is an image, 2. If it is a one-dimensional function, 1. So the fractal dimension in this case is given as 2 minus the slope. A perfectly uniform image would demonstrate no change and have fractal dimension of 2 only. Images with rough texture would have increasing values of the fractal dimension, getting close to 3, but not possible to get to exactly 3. It has to be less than 3. So Yaffe et al. Obtained fractal dimension values in the range of 2.2 to 2.5 with 60 mammograms. So they showed, Bing and others showed that the fractal dimension was useful as a measure of increased fibroglandular density in the breast and related that to the risk of development of breast cancer. And fractal dimension was also found to complement histogram skewness that we mentioned earlier as an indicator of breast cancer risk. So the more variation of fibroglandular tissue of higher density, the larger this factor of fractal dimension. So variability of density and the presence of high density will increase fractal density in this blanket method. So there are some reviews there, we'll skip that. In the Fourier domain also, you can make some, you can derive some measures of texture. The Fourier spectrum of an image with random texture contains the spectral characteristics of the spot involved in the generation. We saw that the spectrum of the texture image looks like the spectrum of the spot. The random input has a flat spectrum and the effect of that is negligible. Thus, the important characteristics of the texture are readily available in the Fourier spectrum. Now, how do you characterize that is another. The Fourier spectrum of an image with periodic texture includes not only the characteristics of the spot, but also the effect of multiplication with the spectrum of the impulse field. So there are the high energy intensity points, as I'll show soon. I think the pictures will show this better. To see this effect better, in some cases, it may be useful to move to the polar coordinate system, FRT. R is square root of u square plus v square. T is tan inverse or arctan of v over u. And change the FUV from the Cartesian coordinates or rectangular coordinates to polar. Then integrate FRT along T and you get a function of radial frequency only. Integrate along R, you get a function of T only, T or theta. So here are some examples. The impulse field. I didn't put impulses at the end. The Fourier transform of that is another impulse field. The Fourier transform of an impulse train is an impulse train, periodic. You have seen that in sampling. But the spacing is the inverse. So this is a circle and its Fourier transform, the Bessel function, except for these artifacts. And a bunch of circles convolving this with that, we get this image, sort of periodic texture, except for the border and the spectrum. The spectrum is, we convolve here, so these are multiplied. When you multiply this with the impulse field you get spikes at those points. So you get this periodic concentration of energy, and the moment you see that, you know it is periodic texture. There is some periodicity of something. If you see such dots. Dots are concentrations of energy. If you convert this to the polar coordinate system, this is angle in degrees 0 to 180 and this is radius 0 to 128. You get this where you again see those points of concentrated energy. If you break that into the marginals, this is a function of radial frequency where the periodicity is clear. But this is a perfectly periodic signal. This is the function of angle, and there is not much variation there because the spot is isotropic. But this shows periodicity. This is the Fourier transform of the fly's eye, and it has periodicity, so you see these spots. It's not as strong as here. You don't see all of this detail. This is a real image of the fly's eye with those patterns that I showed earlier. And converting to polar coordinates, I don't see much advantage. You see some spots here, but I think it's more evident here in this case. And getting the marginals did not really help in this case. This is of the snake skin, the cobra. You see some patterns here that are repeating. I don't see impulses as such, but there is a repeating pattern here. In polar coordinates we get that. In the marginals I was hoping to see more repetition, but it did not work in this case. One of my students tried homomorphic deconvolution of periodic patterns. I'm not sure how well this worked. We tried various patterns, but we got some limited success. Homomorphic deconvolution has been used in speech signal processing to extract one copy of the vocal tract response in the case of voice speech signals, where you have a repetition of a certain pattern, like the vowel A, and you can say this is the convolution with the impulse train, and the basic wavelet is this. So that is copied at every impulse. But there could be some natural variation from one copy of that to another. Homomorphic deconvolution has, can you see that? We should turn the lights on perhaps. In 2D, it's a bit more complicated. Even 1D deconvolution is not easy. There are many pre-processing steps required to achieve homomorphic deconvolution. I mentioned earlier, homomorphic filtering is based on converting the input operation that combines the input components into addition. Here, there is convolution. This is the basic pattern, and there are impulses in an impulse field, and at every location of the impulse, this is copied. This is a building. It's not precisely periodic. There are variations. We wanted to try if it works. It sort of works with some artifacts. So you take a log, you first take the Fourier transform that converts convolution to multiplication. Then you take the log, multiplication becomes addition. Then you apply a filter. A low-pass filter will give you one of this. A high-pass filter will give you the impulse train. The impulse train is difficult to extract even for a speech signal because of noise, and you try to do the inverse weighting after the weighting that is required to get the complex capstrum. The method has practical difficulties. We digitized a cloth with some, a piece of cloth with some repeated motif, this flower pattern, and we got that by deconvolution, extracting one motif out of a periodic presentation of that. Antonio also worked on auditory display of texture, but I won't go into that here. We'll skip that. I'll just show this image to explain one of our projects where we said, as I described earlier, when you are analyzing breast masses in mammograms, what is inside the mass perhaps is not as important as how the mass is interacting with the surrounding tissue, and the contrast between those two regions. So for that, we took the contour drawn by the radiologist and dilated that in both sides, or just say dilated, such that we get a certain amount of the pixels inside the contour and outside the contour. So it's a ribbon molded to the shape of the mass. And then at every pixel along the boundary we drew normals, like computing acutance I described earlier. We drew normals and computed the acutance or edge sharpness measure. And using this ribbon, we computed the Harrelix texture measures. We didn't map this to any other shape. With high resolution, with the sampling distance being 50 micrometers, we get a good number of pixels to compute the gray level co-occurrence matrix. But still, the number of pixels is small compared to the entire image, or even this image, which is 1000 by 900 pixels. So the question arises as to whether we have adequate counts of pixels if the quantization is to a large number of bits. 8 bits should be okay, 10 bits will create difficulties with very sparse co-occurrence matrices. So we showed that reducing the number of bits doesn't help much. You may lose details, so 8 bits we remain there. And resolution of 200 micrometers was found to be good in the classification of masses. 50 micrometers and 100 micrometers yielded poorer results in classification using texture measures. But anyway, our initial work used this. That study was later on. So in the case of a malignant tumor, when we start doing this, this thickness was made adaptive to the size of the tumor. So in this case, not much was left out, but still, that illustrates the ribbon that is computed adaptively. And the normals. That's the original image. Mapping of ribbons into a rectangular band, as done by Sahaina and others, is shown here. Sahainer's paper shows this example where there is a tumor and that's the ribbon. They are taking pixels inside the boundary. We took inside and outside. And they do a geometric transformation of that band into a rectangular or a straight line, and that width is maintained the same. So you end up with a rectangle like this. The interesting thing that happens here is spicules going like that now are vertical lines. When the angle of this mapping matches a spicule, you get a straight line, and you get that. So that observation helped us in designing a similar transformation in the detection of architectural distortion that I'll show you later on. In any case, the ribbon of some arbitrary shape is converted to a rectangular image, so computing the gray level co-occurrence matrix becomes easier, computationally simpler. But these are not the original pixel values, they are interpolated somehow. So that is all I have about texture analysis. If you refer to the, there is another PDF file called texture analysis. This is chapter 7. But the other file on texture analysis has some other examples, some more examples. You could refer to that if you wish. What else should I say? I think that's all I have for today. We said 4:30. Some of you were asking for 4 o'clock. It is 4:15. Compromise. Do you have any questions? We can have some discussion if you have any questions or comments before you leave. I don't want to start another topic for the last 15 minutes. So essentially there are multiple views of texture, and depending upon how you view texture, you may analyze using co-occurrences, frequency domain, representation, fractals, and so on. Fractals will come again later on when I will talk about architectural distortion and other applications. Yeah.
So it's more of an observation. I overheard Sarah say something about a session on, I think, research problem identification or something like that.
Which one?
Research problem identification or something, because like we have some scholars. Okay, so like based on the fact that you have extensively worked on this area, so what's the scope for us? You know, like maybe for research, I mean, those going into PhD, okay, or those who want to do postdoc or something like that. Like how do we identify, you know, an area that interests us? Say I want to continue biomedical or something.
Yeah. That's a bit difficult. I would always say it should be context dependent and locally relevant. And you need collaborators. So the primary requirement is collaboration. So even for my PhD project in 1976, my professor introduced us to cardiologists. We went to the hospital, recorded signals, talked to them, and got some information from them as to how to classify heart sounds or ECG signals. We read textbooks, of course, but talking to the cardiologist helps. And then we have to get the data from patients too. And we need that collaboration. You must have the facility to go and get the data. Nowadays, you have databases available online. NIH, the National Institute of Health in the US, and many other countries require data obtained using their grants to be made public. Even China, they do that. If you get a grant from the government, they say you must put the data on a public database so everybody can use it. Fine. But the data must be annotated. I can't simply say, okay, take these 10,000 mammograms and do whatever. If nobody has marked as to what is it, you need the ground truth. You need a radiologist to mark the tumors or calcification or whatever. Without that, the data will be meaningless. The problem should be relevant to the local experts in medicine. That is, you should talk to them and ask them what are the issues that are relevant to them, where they would need your help as an engineer or computer scientist. If you say, I'll enhance your images, they say, no, I don't want enhancement. If you say, I can detect calcifications, they may say, no, I can see that. But there'll be something that where they need help, and that is where you could contribute. It should also be fitting to the current trend in publishing. Of course, we want to publish. So you need to be in tune with the current trends in publication. Now, the current trend is deep learning. My colleagues have told me without deep learning, you cannot get a paper accepted. So DLC and AI, those things must be there. But previously that was not the case. We use different tools and we publish, but there must be some validation of the results with good data set and participation of the medical expert. You require the right tools and the background, and you have courses in DSP, image processing, pattern recognition, machine learning, or whatever you want to call it. All of those should be available, which I suppose are available everywhere. But the medical collaboration is something very important in our field, in the biomedical field. And the relevance of what you want to do to their practice. You asked about thermal imaging, and I have not encountered thermal imaging in Canada of the breast, but my colleagues are working on microwave imaging, and that seems to be gaining popularity. There are some issues there. The breast has to be immersed in oil for matching of the impedance, and that's not perhaps convenient. In mammography, the breast is compressed, and that causes pain, and that is not convenient either, but that's been accepted. So you want to change it, then you need to see what is acceptable and what is not acceptable according to your mode of or modality of imaging. So it is better to collaborate with medical experts where there is an established practice of acquiring images of a certain type and diagnosis, and then see how you can contribute to that. That's how we have developed all these projects. And in mammography, things developed in a certain sequence. We knew from textbooks in mammography that the calcifications, masses, asymmetry, architectural distortion, they're all signs or manifestations of breast cancer. But if you go back and see the sequence of papers developed and published, you will see calcifications first, easy thing done. And then people started looking into detection of masses. Initially 70%, 80% accuracy, and then it went up to 90, 95. And then they said, oh, we have forgotten asymmetry, but you have to analyze the left and right breasts, mammograms. So then that came up. Architectural distortion was ignored for a long time, and there were some very few papers, and then we started writing papers on that, and then there were more. So like this, a field develops in increments. Easy things are done first, and hard things are left out for others who pick them up later on. As I said, when new students come to me and ask for a project, I say, we should do this. They say, this is difficult. I said, yeah, all easy things have been done. Only difficult things are left for you. And they will get more and more difficult for the next generation as you finish all the current problems. It's not a direct answer. I can't say, do this. But it's an exploration, right? And perhaps your colleagues and for those of you who are students, your professors will have such connections. When I joined IISc in 1976, I didn't know anything about biomedical engineering. I knew we have a heart, but I didn't know about the ECG. I didn't even know what was hardware, software. I said, well, which one is which? And we had never seen a computer, right, until then. So we pick up things slowly. That's what the professors do. They teach us. Professor Ayasan Murthy, my professor, he taught us courses on biocontrol, biomedical signal analysis, and 2 or 3 other courses, instrumentation. And we had courses on all these topics: digital image processing, pattern recognition, speech signal processing. So that way,
We cannot leave mathematical aspect of that to solve that problem.
cannot leave.
That means one cannot ignore or just...
Of course, yes, that's an important point. The radiologist will describe it in terms of visual attributes. Our colleague in radiology just said, well, spicules and there are these parts that are curving inward, and we had to think about how to characterize that, how to break that contour into parts, and how to characterize. It's very simple. Finally, that equation is very simple, but we are proud, well, it's my equation. And it worked to some extent. Concavity is such a simple concept, but it had not been addressed in previous publications. Why? Perhaps they did not talk to the radiologist. And we talked to our colleague in radiology many times on I wouldn't say every day, but we would have regular meetings. Our students would show their results, sit and discuss. It doesn't happen in one day. And then we need to convert that, whatever description they give, in words and pictures. They may draw something. And we said, I would tell my students, throw all of those pictures on the board or on the wall, and let's stare at 100 of them, and maybe some idea will come out. Arrange them, and then you have to turn that into a mathematical algorithm that cannot be ignored, and how you implement in the program, that is the final issue. But you have to write an equation as to how you want to do that. So later on, I'll bring in the retinopathy of prematurity, and we came up with a new measure of tortuosity. Very simple equation, but there is no such method in the literature. And we need to write an equation and say this will capture what you want to analyze and give a number. I use the word encapsulation. That whatever that idea is, you have to turn that into an equation, and that equation should give you a number between 0 and 1 for that measure or attribute, so you can put that in a pattern classification algorithm. You don't want features that go minus million to plus million. You want 0 to 1, and all of them in the same range, so you can put them together. It'll be very hard if you have one feature that goes minus 10,000 to plus 10,000, another 0 to 1, another minus 500 to 60 or something. Pattern classification algorithms may have some difficulties. You can normalize them. But if you can bring them all to a certain range with a good mathematical concept or equation, then that helps. So one is talking to the medical specialist and listening and understanding how they're describing the problem. The other is how to write an equation to capture that. And then implement it as a program. That, I suppose, is not a big deal once you have a mathematical equation. Just a moment, please. We need silence here. Yeah.
Is there any connection between the modality and the textual analysis technique?
Between what?
The type of the medical image and the technique that we use to analyze the texture. Whether the technique changes depends upon the image.
No, texture is texture. So the same method should be able to characterize texture in different types of images. But when texture is not just random texture or one particular type of texture, if it is oriented, for example, and if it is intersecting patterns, like I'll show for architectural distortion, then you have to fine-tune. Any texture, any method to characterize random texture will not work there. You need the directional distribution to capture architectural distortion. Parallax measures will not do that because it's general statistical representation of texture. I'm not putting down Parallax methods, but I'm saying that at first I said no, texture is texture, but there could be specific cases where you may need to design particular transformations. I'll show in architectural distortion again. We transform the region of architectural distortion that was cut off, potential region, into polar coordinates and then computed loss texture features. If you compute loss texture features directly, you may not get the desired result because it looks for waves and spots. So waves and ripples rather. Waves and ripples don't appear in an architectural distortion pattern, but if you map Cartesian to polar, then as I showed in that rubber band, there are straight lines that sort of look like ripples. Then loss method will help. So some pre-processing steps may be required to apply the same techniques to get the desired result when you have some specific kind of pattern that may not fit the original formulation, but after some geometric transformation it may fit better. The basic idea remains the same. So after we finish the next chapter, which will be, I don't think I'll be able to finish it tomorrow. We will have a part of that, and Monday we will finish the next chapter, chapter 8, on oriented texture analysis. Again, I'll skip some parts and show only the most important parts. Then we will take up a few applications from our own research work. So then it'll be a little lighter, and you will see more illustrations of application of all of these concepts. More pictures. A few equations may appear, but they will all be related to what we have seen. So don't miss the application part later on. But of course, you need this also. All right, thank you. See you tomorrow at 9:30.
Two announcements. The first one is your feedback sheet will be on Google Sheet